Yeah.
Here, USB.
Okay, that will. Yeah. Starting. Okay, good morning. Yesterday, I had shown you or given you some indications of how infinite dimensional systems look or begin to look like effectively one-dimensional systems or much lower dimensional systems as a consequence of the fact that there is synchronization. All right? This dimensionality reduction is a technique that we use a lot in physics. Just think about conduction, or think about almost any paradigm of physics. We know that at the heart of the world around us, we've got essentially an infinite number of atoms or infinite number of electrons, or there are infinities everywhere. And yet we come around to either one electron descriptions or one freedom. We have these virtual particles and so on and so forth. So this is a general technique that one must understand is very powerful for us. In synchronization, there is some other thing that is happening which is slightly different. Of course, because the number of particles is not going down or number of elements is not going down. What is going down is the number of freedoms. You take the case of of two pendulums, one swinging on its own and the other swinging on its own. You've got two individual degrees of freedom that are moving around independent of each other, maybe in many dimensions, so you could have even more freedoms. The moment they go into step or out of step, there is some quantity that we have written down either as sigma or as we have written it down as, delta. Those go to zero. So there is some other quantity that gets conserved, if you like, because you can think of that as the derivative of something which has gone conserved, or that one has reduced the dimension somehow, because when things are moving together, it's enough to describe in terms of either sigma dot or in terms of delta dot as equal to zero, which gives you another equation. So there's the lower dimensional representation. Okay? So I would just like you to think that whenever you find correlations developing between systems, or you think of synchronization, I mean, I'm just wanting you to generalize that idea of yours. What you effectively have is a dimension reduction. Right? In the most spectacular case, as we saw yesterday, the Ott-Antonsen brings you from infinite dimensions to 1. But it need not be 1, it could be 2 or 3, and today we'll see some more examples of how these 2 or 3, if not today, tomorrow, one of those things. Okay? So I want to just, this is roughly where we stopped yesterday. I introduced you to the idea that for phase oscillators, the phases lock onto one another. That's more or less all that can happen. There is nothing else. Most systems have both phase and amplitude. When they have both phase and amplitude, if the number of degrees of freedom of the number of equations in your system is more than 3, then very generally you have this phenomenon of chaos. By chaos, what we mean is sensitivity to initial condition. All right? If need be, we can quantify it. But all we really mean by chaos is you start somewhere, you go somewhere, you start very close by, you go somewhere very far away. All right? So the initial conditions play a huge role in chaotic systems, and by implication, well, there's one step in that. Chaotic systems typically have nonlinear equations of motion. Most systems are nonlinear because linear is a very small subset of all possible systems. It's the one that we talk most about because we understand it best, but fact remains that most systems tend to be nonlinear. All right? And this is not something that this was known already to, I mean, everybody. Nobody has ever doubted the fact that the world is highly nonlinear. It's just that one has always looked at the linear approximation because the nonlinear is more difficult to do. And here is an example of the kind of phenomena that cannot be uncovered analytically. All right? So one is that if you take something, you can see that these are oscillations that are really not periodic. And two systems that are coupled to one another, it almost doesn't matter, as you'll see later today. This is a non-unique problem. Right? Yesterday I showed you two different examples of how things synchronize. Let me just remind you again. One was this so-called master-slave approach, where this was the master whose equations were unaffected by the equations of the slave, and the equations of the slave depended on the variable x from the master. So the coupling was, in the language of how when people look at networks and so on, this is a one-way coupling or a master-slave scenario. And you can basically see what the geometry of this coupling is. Now, this gives rise to synchronization, but so does this. If instead of master-slave, I just add in ordinary diffusive coupling, that will also, depending on the strength of the parameters, so I've just added in the same diffusive coupling, that will also give you synchronization. And I want to draw your attention onto the fact that when you have motion which is uncorrelated, it's there in 2 dimensions. The moment you have synchronization, see, these are the variables x3 and y3. So they just go onto this diagonal line, and that's called the synchronization manifold. It's not too surprising, but the synchronization manifold is a lower dimensional subspace. Yeah?
What is this diffusive and diffusive?
When you have a term which is just linear in the coupling, it's called diffusive because it comes from some approximation to the diffusion equation, right? Right. Okay. Okay, so like I said, there are just all sorts. We'll see that this is a highly non-unique problem, all right? You can get many, many different ways of synchronizing things. So with the same coupling for one value of the parameter, you have complete synchronization. Then you can have, for lower values, you have phase synchronization. And I want to introduce you today to the idea of what's called generalized synchronization. All right? One can argue that this is the most common form of synchronization that occurs everywhere. So, proceeding along the line that synchronization means the growth of correlations, this is an important thing to at least understand. Okay, so the first point I just want to make is that if I take a forced linear oscillator, forced harmonic oscillator, one can easily solve these equations, and that's the solution. And I just want to draw your attention to the fact that the solution for the forced oscillator has two components to it, and that's what we call, the phenomenon of beats and so on and so forth. The two components are that there is a response at the original frequency of this unforced system, and then there is a response at the frequency of the forced system. It has both those components. I mean, just a straightforward thing. This is a differential equation that you can solve. Unless, of course, omega is equal to omega naught, in which case you have what's called secular growth. I'm not going to bother about this for the moment. Thinking about a forced oscillator as the following, that if I take your harmonic oscillator here and this is the forcing, I know that the forcing is the output of some other oscillator, right? Because the solution of a linear oscillator is a cosine omega t. So I could rewrite this particular equation as a pair of coupled equations, one for Q and the other for some arbitrary variable y, which has, the solution for this is obviously going to be some a cosine omega t, right? So this gives a certain structure to the system, which is that the equations of Q depend on Y, but the equations of Y don't depend on Q, and this is called the skew product, right? So many examples of such skew product structure are known, and one can basically think of, I mean, the master-slave is one obvious thing, but in situations where you are looking at oscillators, one can imagine that you have, this is the equation of the bath. The bath is unaffected by the subsystems to which it is coupled. I mean, what I'm saying is that this is a common scenario that we think about. All right. Now, instead of having, okay, so this was the case where this is a linear oscillator, right? Now, I can just change the whole thing around and say, what happens if I have a nonlinear system over here, which is coupled to another nonlinear system, right? So if I have one system which is, okay, so this is just basically saying the same thing, that you have some intrinsic oscillation, the force oscillation, you have beats, and so on and so forth. But if I take a nonlinear oscillator, which is forced by some other nonlinear system, this is the kind of equation that I have to look at. All right? So you're thinking of this as your Bath equations, just some, it has its own dynamics at some own frequency, and you're coupled to this. Then, just keeping the idea in mind, the final solution, what is it going to be? The equation for y is going to be unaffected by the whatever happens to x, that doesn't matter. What's going to happen to the equations for q? For q, there's going to be some intrinsic motion which comes from its own dynamics, plus it's going to have something that comes from the forcing, okay? This is called generalized synchronization, all right? If it satisfies a few additional things, all right? So, again, I'm saying that we will consider something to be generalized synchrony if it goes on to a lower dimensional subspace, okay? What's the difficulty? No, I mean, I can see some genuine confusion over here, so. No, I'm just pulling together a chain of arguments, because for most of you, dynamics is not familiar. All right? All I'm trying to say is that, look, when you get things that are coupled, if somehow I come onto a lower dimensional subspace, this is an important thing to recognize, because we cannot deal with infinite dimensions all the time. And infinite dimension nonlinear systems are a pain. So coming down to lower dimensions is, quote unquote, a good thing. All right. So the idea that this is a manifold is just a subspace which has got some nice smooth properties. All right. So yeah.
So when you couple in equations, is it not like the motion is constrained in some sense?
That's
So won't you always get a submanifold?
no,
I mean,
not
suppose
necessarily.
There was no y in the equation
Yeah.
for q and y.
Yeah.
There was no coupling.
Yeah.
Then the phase space is bigger than the phase space of
The phase space is what, right. So over here, let's say Q is in Rn and Y is in Rm, then the dimension of the actual system is Rn plus m.
Correct.
Yeah.
But when they're coupled, won't it probably reduce?
If it, no, the question is that it could reduce by 1, 2, 3. I am going to assert that if it reduces to much smaller,
Much smaller.
yeah, if it reduces to much small, see, supposing you take two Lorentz systems and you're coupling them. One Lorentz is 3 dimensions, the other is another 3 dimensions. When they are synchronized, it comes down to one system, and that's 3 dimensions. So 6 is the space, and 3 is what actually it's in. So I assert that 3 is much less than 6. Right? I mean, because the same argument actually goes for if I take n Lorentz oscillators and I couple them, it'll still come back to the same 3 dimensions. Okay. All right. So let me just show you what this generalized synchronization could look like. All right. So you've got some function x, and you've got a drive, and you've got a response. Right? And once you add the response, you get some signal. Right? The initial signal looks chaotic. You've added a drive to it, and the final signal also looks, by looks I mean I'm going to show you an example, but all possible tests that you could apply to it, it just looks completely random. Right? So one way people have studied this problem is to say that supposing I have two copies of a given system, all right? This picture is not great, but anyway, supposing I have got 2 copies of a system, and what I do is to drive it with the same common force. The response should become identical. And if it does that, then I will claim that this signal and this signal are in generalized synchrony. Okay, I'll come to an example which is a little easier. All right? Okay. Some of you would have been introduced to iterative maps. Yeah, the study of chaotic systems. So let me tell you roughly. This is really a crash course in see, a lot of chaos theory goes on the study of simple mappings where you've got a variable x which, let's say, lies in 0, 1, and this is equal to some parameter alpha so you start with some initial x0, and from here you get x1 is just equal to whatever that solves, x2, etc., and you can just keep iterating this. This gives you a trajectory. And this kind of a map has been studied very frequently, and for a variety of such systems, it's known 4xn into 1 minus xn, so long as you start with some x naught which lies between 0 and 1. Well, you shouldn't start with either 0 or 1. So if you start with any x naught that lies between 0 and 1, the trajectory is completely unpredictable, chaotic, etc. It's so chaotic it was actually used as a random number generator, a pseudo-random number generator. All right? So you take a map like this. Now if you've got a signal, so this is your example of a chaotic system. And what I'm doing over here, right, so I'm calling this function, okay, this is a slight variation on this theme. I've just taken x and n plus 1 is f of xn, where f is this function. And I have another function y, to which I am forcing with x. You see, so the equation of x is unaffected by the equation of y, but the equation of y is affected by by x. Is this clear? Yeah. All right. So as I change this parameter epsilon, okay, so let me start out over here where epsilon is equal to 0, right? X and y are completely unconnected. So here is x, here there is y, there is some, I mean, they do some particular thing. This is the behavior. Some of these curves that you see are really a result of the square root. If I take two copies, one y and another y, right? If I take two copies, these y's are also largely uncorrelated, and they lie entirely inside this unit square. Some of these are because of the functions themselves, but if not entirely uncorrelated, at least the dimension is 2. They're on the square somewhere over there. Right? I increase the coupling epsilon, and now the relation between x and y is some complex object, right? And if I look at y and y prime, actually they're identical. So the equation for y has become some unique function of the equation of x. So both y and y prime are responding identically to the drive. And when you look at the correlation between y and y prime, it's actually on that straight line. I increase epsilon even more. When I do that, x and y become identical. So the drive and the response, so this is the equation for, essentially what we saw, the master slave, that becomes the master, the slave is identical to the master. Right? And clearly the other copy, y prime, is also identical to the master. So then the two copies of the slaves are identical. Okay? It's worth spending just a moment on this, because if you get this, you've got the idea behind generalized synchronization. Namely, so this is the middle panel is really all there is about generalized synchronization, namely that the relationship between the drive and the response may not be some smooth curve, it may not be identical, but it is some unique functional. Yeah? They're just two initial conditions that are, they're independent of each other. You see, what you're thinking of is x is on top over here, x is driving y, x is driving y prime. If the response is a unique function to the drive, both the responses have the same unique function, because algebra is the same, right? Therefore, the two responses become identical. Yeah? The usual example, I mean, not that this is not popular. Okay, the usual example I show at this time is some music playing and people in a discotheque. Especially if there is like a flash dance, flash mobs or something like that. You've got the music at the background and everybody is behaving in exactly the same way, right? without necessarily being coupled to one another. You put a wall between them, they'll still dance. Natu natu, for example. If, yeah.
You give the example of random number generators.
Yeah.
There after a point the sequence starts repeating itself.
No.
That,
See, these for this particular number, right? For this particular map, right? There'll be no repetitions. These are real numbers. This is actually how many have seen Oppenheimer? All the calculations on diffusion inside the core, etc., were done with simple computers, and this was. They say that von Neumann and Ulam actually used this to generate random numbers. Okay, all right. So, okay. So this, any kind of unconnected so-called synchrony. When you look at things which are responding in the same way to the drive on top. In the most extreme case, this could be a source of noise. Okay, X can be just random noise. Yeah. Beg your pardon? I'm sorry, I can't hear you. What is the value of X and value of epsilon in the middle panel? I don't actually remember. In the same, it's some non-zero value. This is for epsilon equals 0. This is for epsilon somewhere non-zero, and this is for epsilon bigger. If you like. Meaning that for weak coupling, you already have this growth of correlations. For very strong coupling, you will have identical stuff, right? Yeah. Okay, so the middle panel is what we are looking at in the sense that if you look at the dependence of X on Y, you can't quote unquote tell very easily that X is correlated to Y. Whereas over here, of course, it's identical, so it doesn't matter. Okay. All right, so as I was just saying right now, if I take two copies of systems where the equations of Y, let's say, obey some, so you think of this Lorentz and this another Lorentz or whatever. If I have identical noise, okay, by identical noise, I just mean that this is simple additive noise. It could even be multiplicative, actually, it doesn't matter. So long as I use the same noise signal to drive both the systems identically, it turns out that they will behave identically. Right? So, okay. Okay, yeah? Not the same distribution. They have got to be identical in time.
Both are getting same number.
They are both receiving the same input. Right?
Yeah. This depends only on the driving force, driving noise.
It depends on the driving noise, but if the particular, at that instant, if the realization is 0.3, then both of them see 0.3. Not that both of them see the same distribution, both of them actually see the same dynamics. I mean, the usual example that one would give, see, in situations where you have a dynamical system driven by noise, common example would be, let's say, inside a cell or something like that. You've got a cell, chemotaxis, you all had lectures on chemotaxis. All the cells are having the same ambient environment that they're looking at, but all of them are to receive exactly the same input. Not statistically the same input, but exactly the same input. Okay. All right, so the idea about the synchronization manifold, yeah?
Are you saying that they receive the same realization of the random
Yeah.
noise?
Yeah, the same realization of the random noise is input on both of them. Yeah. Okay, so the idea about the synchronization manifold is the following, that you have a space, once you become synchronized, you typically stay on that synchronized state of synchrony so long as it's stable, and we'll see what to do to make things stable. Right. Now, this has a dimension which is lower than the overall phase space. As I was just discussing, the dimension of x and the dimension of y could be n and m, and the overall phase space would have dimension n plus m, and you go to a much lower dimensional subspace. Now, thinking of the synchronization manifold as some kind of a surface in this lower dimensional space, stability for synchronization actually means that you stay on the synchronization manifold. So any perturbation away from the synchronization manifold, you should come back to it. Right? On the manifold itself, your dynamics can be bizarre and chaotic, and it can do whatever it likes. We saw the Lorentz system. The dynamics was actually chaotic inside each of the Lorentzes. It is just that the joint motion was identical, and that was stable. Right? So you've got this surface, and you want any perturbation that I push away from that surface, I should come back to it. On the first day when I made you hear the synchronization of those metronomes, we saw that it came to some stage, and then there was some little perturbation that pushed you off, but then you came back onto the synchronization manifold. All right. So there is, I've given you in the reading material the papers by Josic. This is a sort of a mathematically well-developed subject. There is the property that a stable synchronization manifold should have is something called K hyperbolicity. All right, and it's not always a manifold in the sense that sometimes these surfaces are not differentiable. So it could be a more complicated relationship. But let's just say that today I will just talk about smooth surfaces. Okay, so there's some issues to do with differentiability and non-differentiability. Okay, so I'm saying really the same thing again. All right? Okay. Yeah?
Say initial conditions and noise, will it be possible to predict in all circumstances when this synchrony is going to happen?
See, the time of synchrony is not something which is typically under one's interest or even control. Okay.
But isn't it important for biological systems?
Yeah, we'll see that, the time scale of synchronization is not, in a sense, not a relevant parameter. Right? Yeah. Okay, I'm willing to change my mind at some point in time, but for the moment, let's say that I'm not. Right. Okay. So the whole thesis that one is saying is that when two systems are in a generalized synchrony, the variables of the two are correlated in some way. And I will just assert that there is a functional relationship between the variables of one system and the variables of the other. Okay. Some functional relationship. I'll give you examples, but this is not either exhaustive or even meant to be, because these things cannot be. Okay. If they are in perfect, okay, so here you've got two copies of systems. Two systems. One is in X with its equations Fx. One's in Y with its equations Fy. They could be the same, need not be the same, whatever, doesn't matter. If they are in perfect synchrony, then you want this functional relationship as the identity. You want X to be equal to Y, that's what perfect synchrony is. Okay? So the question I'm posing is to flip it around and say, supposing I use two coupling functions over here. Okay, so here I've got X and Y independently. I add two coupling functions all right? I want to design these two coupling functions such that I get phi x minus y is equal to 0, okay? See, one approach is to just say I've got two pendulums, they are hanging on a beam, this is the Lagrangian and the coupling is whatever it is. Flipping it around, I've got two pendulums, they're not hanging on a beam, but I want them to oscillate identically. So how do I couple them? Okay, so here are I've got to find these two functions. All right. Now, if I make supposing I put this equal to 0, then x evolves independently, y depends on x. So that's the so-called master-slave scenario, the drive response scenario that we've seen. All right. Now, the drive and the response, so in the most general case now, I've got just some two arbitrary systems in variables x and y. Then this functional, so, okay, so there's a lot to all of this stuff. And I've got, in your references, you will see some discussion about these issues. And I just want to point out how one can do a constructive way to synchronize systems. Okay, supposing the relationship that is, so I'm just changing notation a little over here. The variables of the two systems are x and y, and I subsume them into some capital X. And this relationship that I had, that phi of x and y, etc., is equal to 0, the functional relationship between the two, I'm just reasserting it as some other function for which I need a 0. Okay? And the idea is in a sense, very simple. If inside my phase space, I've got some low-dimensional submanifold that I want to come to, I'm usually at some arbitrary point. What do I need my coupling to do? One way would be to say, I'd like my coupling to bring me onto the submanifold, right? I want to come down, and once I am on the submanifold, I don't want to escape. So if I look at the flow equations, when I confine myself to the submanifold, I want them to be orthogonal to all the normals. So thinking of this as the synchronization manifold, I'm in arbitrary phase space, my coupling should bring me over here. Once it has brought me over here, the resulting motion should always be orthogonal to all the normals. If it's orthogonal to all the normals, then I'm going to be stuck on the surface forever. In a sense, that is about as simple as it gets. So the normals are given by the derivatives of the surface, and I define a vector of normals. Here is the initial flows, etc. And you get a condition like that. If that was the case, we'd be home and sailing. This requires some engineering, namely you need to put some algebra over here by putting in the coupling. See, this doesn't happen automatically. You need to add these coupling terms so that this happens. And that actually gives you a nice equation for what is the coupling. Okay, so this is the coupling terms. So the way in which it works is that the coupling should be exactly equal to, it should satisfy this particular equation. All right? This is just algebra. And unfortunately, in the sense that, you see, these are not square matrices, because the dimension of x and the dimension of y and all of them is different. So it turns out that this equation, or this set of equations, has got many, many sets of solutions. And it's up to you, actually, or up to the person who's interested, to do the engineering this way. I'm going to show you examples of how we do it for interesting problems of a certain kind, right? Okay, so this coupling is guaranteed to bring you onto the manifold that constrains the flow. You may, you note that the coupling is only defined up to addition of terms that will vanish on this manifold. So, I mean, like all constraint problems, when you study the theory of constraints in classical mechanics, we know that any number of terms can be added to the constraint equation so long as they vanish at the constraint point. Additional forces. Okay, so that's what all this means. So you want this kind of algebra to go on, all right? So I'm just giving you the same argument now for a surface which is not necessarily, as an example of the table, flat, but curved. Okay, so this is basically the idea. You've got this motion moving around in some arbitrary space, bring it down to a lower dimension and keep it there, and keep it there by requiring that effectively, I mean, it's difficult to not use words like force, but these are not forces. These are just the additional things that come from the coupling terms. Okay? All right. Now, in addition to everything else, you require that stuff should be stable. And stability basically just means that eigenvalues of some matrix should be negative. I'll spare you the details because this is straight out of dynamical systems theory. These are, the rate of separation of initial conditions is called the Lyapunov exponent. Now, when you confine it to directions which are normal to the surface, these are called transversal Lyapunov exponents. So what you want is that in all transverse directions, your motion should be confined, whereas in the motion of the manifold itself, they need not be negative. So there's some mathematics over here. Right? Okay, so to give you an idea, see, the example that we had, that I had shown you was of two Lorentz systems where master-slave coupling, and I brought you onto a submanifold where x1 was equal to y1, x2 was equal to y2, and x3 is equal to y3. Supposing, for whatever reason, I would like x1 to be a times y1, b times y2, and c times y3, where a, b, and c are not equal to 1 necessarily. All right? Namely, this synchronization manifold is not some diagonal line, but some arbitrarily inclined, any old line. All right? Then it turns out that you go through all the algebra that I've shown you, all right? And you come up with this very nice, well, very nice meaning the algebra all works out, and you can make a choice that this is one coupling, that's the other coupling. Now, even if I put A equals B equals C equals 1, this is not master-slave, this is not diffusive coupling, this is not anything, this is just some new coupling, and yet what you will find is that if that's your original system, right, the way using arbitrary values of A, B, and C, in fact, I think I used 1, 2, 3, my usual password, all right, Lorenz 1, 2, 3. If you want to hack my account, all right? So anyway, the point that I want to make is that this is a constructive procedure. You tell me the manifold, I'll tell you the coupling, right? Because it is highly non-unique. There are many, many ways in which I can do this for the case A equals B equals C equals 1. Yeah? And what effectively one has to do is to solve this equation. And because it is, these are not diagonal problems, even over here this is 6 by 3, then it turns out that you can choose things in many ways. You can have a lot of fun, right? Okay. For such systems, it turns out the oscillators don't even have to be identical, right? So I can make This is an old picture, it's faded. Right, I can do it for arbitrary different systems, it doesn't matter. Okay, now the important thing is that this manifold doesn't just have to be a linear subspace, right? I can ask, is this possible? Can I make x equals, this variable the same, this variable the same? But in the third case, I would like the relationship to be quadratic, right? So there are two ways in which this can be quadratic. One is that x3 squared is equal to y3, or the other way is to say that x3 is the square root of y3. Both of them have the same quadratic relationship, right? And again, it turns out to be very, I wouldn't say trivial, but it can be done in at least three different ways. One is to make x the master and y the slave. You see, these are the two coupling terms. So a zero vector says basically that the second system has no effect on the first. All right? So this becomes master-slave. And here are the two, I've plotted this with the logarithm on this side. And you can see that x and y are identical, but the third variable is just squared. And when you plot it in space, in some appropriate subspace, you can see that the curvature automatically comes in, the quadratic curvature comes in, right? But I can choose this coupling in arbitrary different ways, and here are at least two more variables, ways of doing it. One is to make it the slave master. Okay, so you see, this was master over here and slave over there. Here is slave over here and master over there. And here is a little more democratic. Both of them are equivalent, etc. The point is that you've got this synchronization manifold. One coupling can bring you here, another coupling can bring you here, a third coupling can bring you somewhere else. All right? So this is highly non-unique. The whole process of synchrony is a non-unique problem. Okay. All right. Okay, so all of this is in a sense trying to work towards how does one apply it in much, much larger systems. All right? So one application, right? So initially I'd done this work on designing generalized synchronization, and I was giving a talk at the last, not this StatFizz, the one before that, which was like some distant past. And somebody in the audience said that, would this apply to micro swimmers, or would this apply to birds, or some such thing like that. So we thought about it a little and said yes, because you see, each of these birds, let me just explain this picture for those who weren't there in some discussion yesterday. There's this photographer called Xavi or Javi or something, Boo, and he has a very nice website, so I would invite you to go look at it, apart from which he's allowed me to use his photographs. What he does is he takes pictures of birds flying and then analyzes it frame by frame, superimposes them on the trajectories of the birds. All right, I have more pictures, but for the talk I just took one. So this is not okay. So this is an individual bird that is flying, and this is a time-lapsed superimposition of the flapping of the wings. Right? So the bird itself has a trajectory in three-dimensional space, so three variables over there, right? X, Y, Z, and velocities. There are internal variables, which is the flapping of the wings. And the flapping of the wings is periodic. So you see there's an oscillator associated with the bird's, the internal variable of the wing. There's this variable of the bird itself flying that is in 3 dimensions. So flocks like this, you all must have been exposed to all these ideas over here, flocks can be up to 1 million particles, million birds strong. And they all avoid each other, right? So they maintain some spatial separation. There's all sorts of, swarming algorithms that people have used, Vichek algorithm or whatever, I don't even know what things are. Okay, but when you look at this, particularly if you look at these two, see, these two birds have got to maintain a certain fixed distance from one another. They're at different heights actually over here, right? That's why, okay, and there is this sort of very peculiar ordering phenomenon that is visible over here. That is, there is a separation between, and all this is happening at huge velocities, right? Because these birds are flying very, very fast. In murmurations, the individual velocities can be quite rapid. All right, so you need spatial separation, and the internal oscillations must also not be, they are clearly synchronized. So this is a good case for applying ideas of swarmulators that, that we talked about yesterday. Right. But the question is that given arbitrary particles moving in three-dimensional space, can I keep them at a fixed distance from one another, right? And it turns out that you can.
So there,
Big one?
I mean, some birds seems to be in phase and some birds seems to be out of phase, right?
Oh, absolutely. I mean, they could see. Yeah. Then, first of all, they're not coupled, right? All I'm saying is that for these flocks to happen, there can be no collisions. So I would like them to be able to move through space, keeping, let's say, a fixed distance between each other, right? And then there is a phase relationship that develops, but the phase relationship that develops between these individual flapping is due to hydrodynamics, because they're moving through a fluid, and if they are completely out of phase, that actually makes the flow turbulent. Right? So when you see lots of birds flying together, you'll find that the phases of their oscillations actually have a nice relationship between them, and that really comes from the fact that they are catching the wind stream from each other. Okay. Okay, so there's just some algebra over here saying that if I have two systems which are x and y, the same, that I want to know what is the coupling y that will make this relationship happen. And there is a very trivial way, I showed you one set of algebra. There's a trivial way in which you can do it, namely if you take the second coupling to be this quantity over here, if you take the second coupling to be that quantity over here, then without too much difficulty, this algebra tells you that d phi by dt, this phi, just the variation of phi x minus y, it turns out to be just minus r times that quantity, and where r is some arbitrary constant that you add, and this actually converges exponentially fast. So, so you can design this to happen very fast, but then you pay a price. And the price that you pay is that the original dynamics, this f of y, that is actually gone. All right? So, this turns out to be the new equations. And these new equations, the original y is just vanished because of the way in which you couple the system. This is a bad thing except in one case, and that one case is if the desired relationship is a linear relationship. Namely, if you want things to be just constant separations from each other. All right? And this constant separations from each other is just represented by. So then this becomes a case of the leader and the follower, and the way in which the leader and the follower can ensure that there is a constant separation is that they both have the same velocity. which is essentially the same argument that is used in the Wycheck algorithm. The velocities have to become identical, all right? And there it's in the initial conditions that things are separate. So the point is that, okay, so in this particular case, this actually works. And I mean, here's just to show you that you can do this. I can take two systems, couple them through this particular way, and if this is the dynamics of one, that's the dynamics of the other, and the two of them are keeping a distance apart, right? Actually, you can do a little more. You can just take some arbitrary trajectory in three-dimensional space. Oops. And you can have, you see, the point is that this dynamics is now constrained. Even though I've got some, in this example, I've got 20 birds. So this is a 60-dimensional configuration space that I'm talking about. 20 birds in three-dimensional space, 60 dimensions to worry about. But now I've confined them all to have a certain fixed distance from each other. Right? So they're moving essentially like a single object. Right? This is now a single object which is just moving. So the dimension has come down to 3. Right? And yeah.
Even in real life case, like there is some sort of, what to say, like there could be a lag of motion.
Yeah.
Would be only accounted if you consider some sort of fluctuation.
Absolutely. No. I'm not claiming that when you see birds flying around that it is just a... But all I'm saying is that if you've got 1 million birds, the configuration space is 3 million. Right? Just keeping all the velocities fixed. Just don't worry about it. It's 3 million. But the whole thing is moving together. You've seen those, I've seen those pictures of those murmurations and what have you, right? Or maybe it's worthwhile to just go back and so here is a typical example. You've got 1 million birds over here. Of course they are, there are all these other aspects to it. I'm not saying that this is a rigid body moving in 3 dimensions. But this is not a 3 million degree of freedom system. It's not 3, but I would just claim that it is something closer to, 20. If not 20, even 100, even 1,000 is much less than 3 million, right? So if I think about what the variables are, if all the interparticle distances were fixed, then it's obviously a rigid body, right? Any arbitrary rigid body has got an Avogadro number of particles in it.
Even in that equation, you can just introduce a very small kind of fluctuation.
Which actually I have done. The trouble is that, see, where do these ideas apply? They apply, for example, well, actually, there's a point of, just a historical point. When we first did this work and we showed that we were able to get all these to, move in exactly the same trajectories, we found that there was a patent on it. The patent was applied for by Airbus because this is crucial to their algorithms to avoid plane collisions. A version of this same algorithm is used to avoid collisions and we've actually applied this whole thing to robots. How do you get robots to move in correlated trajectories without colliding into one another, and drones? In some talks that I give, I've shown pictures of these drones which use our algorithm to avoid colliding and keep the same trajectory. Right? One second. Okay, so just this last part.
Yeah, I had a question.
Yeah.
So there was a comment on in the time lapse image that you showed
Yeah.
of birds being out of sync.
Yeah.
Just by looking at the time lapse, we cannot tell that they were flapping their wings out of sync, because that would require the positional information also.
That's
If
right.
they're out of sync, but they are like half a wavelength apart, then they might be in sync in their wave flapping, but in this picture it will look out of sync.
See, this is, I mean, this man is a photographer.
Yeah.
Right? So, and I actually, I mean, when we had done our work and whatnot, I shared those images with him about whatever, and he was just kind enough to let me use his pictures. What we need to do is exactly that. I don't know the various heights of the birds. I don't know how he has done the superimposition. I mean, he may have actually doctored the pictures, for visual. I mean, he sells these as 200 euros a photograph, right? So all that is to be taken. I mean, I'm just motivating why one would want to do this idea of swarming and sinking. Because it seems to be a crucial way in which real life systems do interact with one another.
So just one more question.
Yeah.
I may have missed something, but eventually the result that you showed is where all particles have identical velocities, right? But
Yeah.
that's a much stronger constraint than actually just having fixed interparticle distance.
No, in order to have a fixed interparticle distance, they have to keep that the velocities identical. Think about marathon runners. Meaning that if you want to keep a fixed, the pacers, the ones who give you the pacing in long distance runs, you keep a fixed distance from your pacer. And it's only at the last point when the pacer moves out that you spurt and you go ahead, right? So, if you want to keep that same constant velocity as constant separation as you're moving around a track, the way in which you do that is to have the same velocity.
So all particles pairwise, the distance is fixed.
Yeah. This was a little bit of an artificial problem. Okay, so, that just basically tells you that that the velocity of x and the velocity of y have to be the same, all right? So this is and that is the constraint. Sort of, they keep the same velocity and they keep a certain constraint, right? So, anyway, so let me just show you this again. There is little noise in this, except that you can't see it on that scale, all right? Our idea over here was more to have an arbitrary flow through space rather than to say that it's on a Lorentz attractor or any other kind of an attractor. There's just some arbitrary trajectory that I drew in three-dimensional space, the blue one, let's say, and every other thing is following that. Okay. All right, so, yeah. Big one?
Flock, when it's moving, it's likely that a bird is going to follow the motion of the bird in front of it rather than on the sides or behind. Is that accounted
true.
for?
See, now, I've just sort of given an illustration that it's like a bird thing. What we have applied it to is a single particle which is a master and all the others are slaves. Right? The master could have just said, there's one single leader and many followers because we apply it to autonomous vehicles, things like that. with birds, I mean, I actually don't know what's going on inside the nervous system or the brain of a bird. So it's not clear to me. I mean, people say that Parisi has all these results that a bird looks at seven of its surrounding ones, or is it only looking at the ones in front, or how much peripheral vision that it has, etc. So there could be, one can add a lot of stuff onto this. I'm just sort of bringing the idea of flocking of arbitrary particles into the language of swarming and sinking, right? The sinking is a spatial sinking rather than just temporal. Obviously, there is a temporal component to it also, but the spatial part means that, now the idea of swarmulators is not just that you synchronize the internal variables, but you have a spatial synchrony between the spatial variables also. Yeah? Okay. All right, so actually, all right, now so far what I have done is to introduce ideas of synchronization, phasing, the simple models of phase oscillators, and then generalize it to more complicated oscillators, perhaps chaotic oscillators, and shown you how the notion of synchrony can actually expand. And the whole idea about generalized synchronization is that when you've got dissimilar systems being driving each other or coupled to each other, huge correlations get induced between these variables that become evident if you look at the dimensionality of the motion, right? So looking at things in terms of the synchronization manifold is very helpful. Now, given the fact that any two copies of any system will not be exactly identical in terms of parameters or any such thing, the idea of generalizing the notions of synchrony is extremely important, right? The other part is that in biology in particular, you have a lot of different kinds of oscillators. It's not just that they are not identical to one another, but they are also different of various different types. So when you think about the sort of very sensitive ways in which a lot of biological phenomena take place, it's inevitable that many of them have to synchronize not through the normal, ordinary, pendulum synchronizing or Kuramoto or some such thing like that, but it has to be a lot more general than that. Because otherwise, stuff would never get done at the cellular level, that is. Stuff would just simply not get done. Think about it, about the few thousand oscillators that are there in each one of our cells, and yet I'm able to move my hand, I'm able to direct my hand to move, even though it requires so many different individual actions to have happened. Okay, so it's something to think about, that the notion of synchrony needs expansion. Okay. Now, I want to talk about two things. Today, I will just introduce an idea to you and come back to a discussion of it tomorrow. So the two things that I want to talk about are chimeras and amplitude depth. All right. So a chimera is a animal that was, it's a Greek word, animals that were mixtures of various other animals, all right? Our mythology is filled with chimeras, most famous being Ganesh, whom we just celebrated a few days ago. Ganesh is a human, the human body, elephant head, prime example of a chimera. All right? But these were mythical objects with various different parts. So this was used by Stephen Strogatz, who has been very influential in this field, to describe the following situation. Supposing you have a system of n oscillators which are identical, phase oscillators, all of them are acting identically on and are coupled identically with each other. I've spent a lot of time to try to tell you that when they are all identical and they come together and they are all interacting identically, the dimensionality reduction is such that all of them behave like a single system. Right? That's what the whole Ott-Antonsen was about, or the idea of the synchronization manifold is that you come to a much lower dimensional phase space, single dimensional. In the sometime in the 90s, Kuramoto and one of his postdocs called Batog Tok, it's a Mongolian name, they discovered a phenomenon in coupled Ginzburg-Landau equations, right, where again, with a lot of dimension of whatever reduction, it comes down to the study of oscillators of the Kuramoto type, phase oscillators. But the coupling is a little different. And what they saw was that instead of all of them eventually behaving identically, which is what we saw in the Kuramoto case, suddenly there was a spontaneous symmetry breaking. And the symmetry breaking, I'll just show you what the symmetry breaking is like. It looks something like that. So we've been seeing this idea of synchronization where all the phases eventually become identical, right? They all become the average phase. That was the whole idea of the Kuramoto order parameter, right? So you've got this average phase, all of them come together and they get into the state of the same average phase. What Kuramoto and Batog Tok discovered that if you have a coupling which is non-local, and I'll just come to what is meant by non-local, then identical oscillators coupled identically still showed dynamical symmetry breaking. So this is what is meant by non-local coupling. So local coupling is just, let's say, nearest neighbors, or at best next nearest neighbors, or something like that. This is the global coupling that we've been talking about in the other forms of the Kuramoto problem. And non-local coupling would be, let's say, something like this. You could also call it non-global, but it's just a choice, all right? So typically, if you have things that are coupled in a distance-dependent way, such coupling is termed non-local, all right? So what one does is that you have a, okay, so now I've just written the continuum version of this. So that's your phase oscillator over here. And so it's phase, frequency, and now I'm just coupling it to all the others. The coupling kernel over here, G, it depends on the distance between, see, in the normal Kuramoto case, Gx minus x prime was just 1. It was just, all of them were identical, all right? So instead of that, if I couple them in this way, it turns out that at some particular value of the coupling, you have the oscillators break into two sets, one set which are almost all coherent and of essentially the same, okay, the phases are not identical over here, but you can see that all the phases are very closely related over there. And for this group of oscillators, right, the phases are just all over the place. So it's like the coexistence of order and disorder. And this has been a sort of fairly active area of interest, because the reason for this kind of spontaneous symmetry breaking is, let's just say, poorly understood as to what motivates this kind of breaking of symmetry, because there is really no difference in the way in which oscillator number 500 or the oscillator number 1000 is coupled to all the others. They're all coupled identically with each other. Right? So I'm not going to. I will discuss this at some length tomorrow because it's a little detailed. But the form of the coupling of this kernel, yeah. Big one. Okay.
Is it related to the frequency of the oscillator, like too high?
All of them are, we'll take them to be the case where all of them have the same frequency. I will put all the omegas equal to 1. In fact, no, I'll put them all equal to 0, for example. If I just remove omega from the game, which you can do by some rotation, it doesn't matter.
So it has to do with the network properties.
It has to do with actually this non-locality in the coupling. The moment you go to local coupling, you don't have a chimera. And if you go to global, we've already done the analysis yesterday and the day before, and you don't have chimeras either. So this very peculiar kind of, or rather this just induces certain differences in the coupling, which then give rise to thing, right? Okay, so there's a lot one can do with chimeras, right? Because this non-local coupling kernel has this kind of a dependence on it. So here, for example, is a function that looks like a hat. People have used cosines. People have used anything which has a certain kind of distance dependence. People have applied. This actually is from my own work. My idea was not very successful. Well, it had mixed success, let's say. I thought that by having linear decays, one could do the analysis a little better. But I'll explain some of it tomorrow. And you can play around with the kind of coupling, and you can get any number of coherent and incoherent regions. You see, in the simple chimera, you have one coherent region, that is the ones on the side, and one incoherent region. But with changing the design a little, you can have two coherent regions and two incoherent regions, and so on and so forth. These are called multi-headed chimeras for sort of obvious reasons. Okay, and I want to just conclude by showing you what a chimera looks like. So if I've got, see, in the usual Kuromoto problem, you had all the oscillators eventually going together, right? When you have a chimera, you have some group of oscillators that behave the same. For example, all these are by and large the same. And you've got another group which is incoherent. These are not static. That is, all the oscillators that are coherent will not always forever be coherent. Some of them could join the incoherent group. So these are breathing objects. Yeah? Over here, it's just it's just phi dot.
Okay, it's phi. Oh, okay.
See, so you've got your oscillator index over here, and you've got these, it's just here's your phi.
Mm-hmm. Yeah.
And as phi keeps changing, what you're seeing over here. So by and large, these ones will stay at whatever value they are. And by and large, these ones will be all over the place. So,
Yeah, now I see, yeah. Yeah, I mean, now I see the baseline, like the line is situated like at non-zero, then I see it.
Yeah. This is just taken at some realization. No, but what's to tell you is that like the coherence regions don't always, I mean, these are evolving configurations. Some of these are, with 100, it's really difficult to see. You would need to somehow see a large number of oscillators that will behave in the same way. This is the simplest one. So here you find that all these are remaining nice and coherent. These ones are going, and the ones at the edges, eventually they leave and come back. All right. So tomorrow I will discuss an example, at least some examples of how these space-time patterns, this is an unexpected, I mean, it's unexpected in the context of what you are, when you're looking at these kinds of systems. But I'm just saying that the reasons for the spontaneous symmetry breaking are not completely understood, although I've given you in the reading material, there's a very nice paper by Omelchenko in nonlinearity, which you might like to look at. Okay? And then tomorrow we will discuss some of these in a little more detail. Okay? Sorry, I'm finishing a little early today, Sanjeev, but this seems a natural space to stop. Yeah.
I'm asking that, like the Malaysians are walking line with collective behaviors. I'm just saying, what if it breaks, like some of the, like say a bird was like went away from that group, how will it affect the group? Or say like a fluctuation or something like that from noise from outside.
See, there are two common fluctuations that happen in murmurations. Okay? The most common one is that a predatory species comes and tries to eat one of the birds in the middle. There you will see the whole thing just, splitting, separating, moving around. So in most of these flocks, there is no single leader. Right? So that's...
The group just scatters.
Yeah, doesn't just scatter, it separates.
It also form other groups and then they also...
And then they will sometimes merge again. If you've never seen anyone from Indore, no. No, I remember once sitting outside Indore railway station and seeing a flock of pigeons. And it was like a huge flock, at minimum of a few thousand birds. And I, again, I remember seeing these things just sort of flying into a building, separating around the building, and then reconverging on the other side, and and flying around. What I'm saying is that this doesn't require you to go to England and look at some starlings in a field. They are there over here, and once you just have a sufficiently large flock, you'll see the same kind of phenomena where they merge, reconvene, and so on and so forth. Yeah? Yeah?
Like in the Vichak model, we can have this tunable parameter that gives us from an ordered state to a disordered state.
Yeah.
Is something of that sort possible over here, where by changing some parameter we can go from a coherent phase to an incoherent phase? I mean, this synchrony is broken.
In what, in the chimeras?
Yes. No, not in the chimeras. The previous example of the birds.
Oh, yeah. You've got the coupling parameters always there. You just add it and you go from coherence to incoherence very fast.
And
Yeah.
also, how in that example only, how do you incorporate, say, a predator coming in and everything's...
Those are more complex problems. I don't know how to do that. Yeah.
Thank you.
Yeah.
With these chimera states, are there experimental realizations
Yeah.
in physical systems?
Again, in the language of introduction to a paper, the problem has been interesting for many years, etc. Some animals apparently, and that also includes students in a class, sleep with, half the brain is asleep on one side and the other half is awake. And then apparently, especially dolphins and stuff are supposed to have this hemispheric or semi-hemispheric sleep or something like that. Half the brain is shut off and the other half is alert. I mean, it also goes for lecturers, right? So it's not just students. No, but jokes aside, this was a common motivation for the study of chimeras, was to say that, look, you have this situation where you could be half asleep and half awake. So a lot of brain activity on one side, complete death on the other side, and then switching from that is a common example. Yeah. All right. Yeah, I'll come to this tomorrow.
We'll have just a group photo downstairs. Okay, just so maybe before coffee we can have the photo and then.
Okay, so we restart the lectures, and I'll try to finish as quickly as I can the lectures on the mean field theory approach to move into three-dimensional models for glasses and how different they are from. Perfect. Thank you. How different they are. So, just to finish the story we had yesterday, so the summary of the lectures were I described some mean field models for the glass transition, then went into the dynamics, into the statics, then discovered that there was these two temperatures, dynamic and Kurtzman transitions, and then that was all, in a sense, reinterpreted or digested by the Franz-Parisi potential. So we have defined it's the free energy cost to have fluctuations of the overlap Q, and then you take the log of the probability distribution function, and you have the free energy that develop this secondary minimum becoming like the stable states below the Kurtzman transition. Associated to this, emergence of a configurational entropy that goes to 0 at decay, and the abrupt discontinuous increase of the order parameter between the liquid and the glass phases. And again, just to emphasize, to repeat the questions we had yesterday, everything here assumes thermal equilibrium. We do statistical mechanics computations. So that's what the Boltzmann distribution would do to you if you could maintain thermal equilibrium to arbitrary low temperatures. So of course, we saw in the first lectures that to do it in practice, because of the timescales problem, it's complicated. But at least this is what statistical mechanics is telling you. So I want to finish that short story. I wanted to do it yesterday, but so I tried to make an analogy with what you learn if you open any textbook on statistical physics. So I did the exercise this morning in the office. I was given there are 4 books on statistical physics. I opened them at random, and you find that type of things in all of them. So it's really basic stuff for phase transition. And this is what you have when you study the van der Waals equation of state for liquids. You have, because of the attractive forces that van der Waals adds to the, the law of perfect gases, you have attraction, you have a transition between a liquid and a gas. It has all these features, and within the van der Waals approach, you compute everything. And so this is when you learn about first-order phase transitions when you are at school as babies, okay? So that's a bit like the same framework. You have this metastable state. We said the free energy difference here is directly related to the configurational entropy. So the analogy with the liquid gas is what I want to use now. So imagine that now you are in this temperature regime, and you know that the glass phase, which is happening for fluctuations of the overlap that are finite, it's not the equilibrium state. If you look at your system, you will see the liquid and never the glass. But you know that you can do something in thermodynamics. You can introduce fields conjugated to your order parameter. And this is what you've learned, again, when you've learned thermodynamics and statistical mechanics. You can do Legendre transforms. So, for instance, for the simplest system, you move from controlling the volume to controlling the pressure, because you know that pressure and volume are thermodynamically conjugate variables. Temperature and entropy are the same, and this is when you move from energy to free energy to Gibbs free energy, depending on what are your control parameters. So you can do the same with that game, and they have played that game a lot. So instead of thinking of Q as my control parameter of my variable, I could introduce a field conjugate to this. So I could introduce, in a sense, a perturbation to the field, which is minus h time Q, just like you introduce a magnetic field with the magnetization, minus h to m, so you control magnetization, magnetic field, minus PV when you go to the enthalpy, etc., etc. You can play the same game and change variable between Q and a field which is thermodynamically conjugate to the overlap Q. So it means instead of working with that thing with depend on Q, you would introduce some kind of, Legendre transform of that guy, which would be just, V of Q minus epsilon Q, which is the field conjugate to Q. So again, don't ask me how to do it in practice. I don't want to know. I'm just doing the thermodynamic constructions that you've learned before. I introduce the field conjugate to my order parameter, and I use that epsilon to control the value of the order parameter. So why do I do all this? I mean, it's interesting to think in terms of those variables. So if you introduce that field epsilon into your function, the field epsilon, when you get it large, to decrease the energy, what you'll have to do, you will have to increase Q. Okay? So if you work at this type of temperature here, where the low Q state is really the one that's equilibrated, and the high Q state has a larger free energy. But now you start to play and you introduce your field here. So you're going to force the system to go towards the large Q. And so what you're actually doing here, you're adding, a linear term, which is this minus Q, to this function. And so when you increase the value of epsilon, you're going to tilt and tilt and tilt and tilt your potential at this temperature above the transition. So in a sense, you are forcing the system to fall into the high Q regime. So if you do this in the high temperature thing, what you're going to do, you're going to tilt your parabola like this, and it's going to tilt, and you have a gradual increase of Q. So you increase epsilon, Q is going to increase, but this is going to be very gradual. Nothing interesting is going to happen. Of course, the interesting regime, and when you're here, if you gradually tilt this potential, this one at some point is going to cross below. And then the system is going to jump discontinuously. So what you will eventually do at these temperatures above the Kaufman transition in the liquid, you increase epsilon, and you will see a first order transition towards the large Q. I take your question at the very end, please. So it means I can now work in this extended phase space where I would have this temperature axis. So I'm decreasing the temperature there. And then I'm playing with this new field that I've just introduced, which is, again, in the calculation, just the field thermodynamically conjugate to Q. So when we just decrease the temperature again, so we've, for the 10th times of the lectures, we have these two dynamic and static transition temperatures. And this is the physics we've done so far. We have studied the physics of I'm cooling a system without thinking about this epsilon coupling field. And that was the thermodynamic transition towards the glass state with the finite Q thing. Now I'm telling you, I'm just above Tk, I use epsilon, I'm going to tilt, and I'm going to make the state with a large Q the stable one. And so you can imagine what's going to happen is that out of this, there is a line of first order phase transition that's emerging. Okay? So again, I'm here, I tilt, and I jump discontinuously between a phase where Q is 0 and a phase where Q is larger than 1, it's finite. And when I do this, I'm just crossing the first order transition, just like you do when, again, you think about the van der Waals equation of state. You can have this line of first order transitions. And again, pushing the analogy to the liquid gas, you know what's happening as you increase and increase and increase the temperature. There is a moment where you lose that thing, so it means the first order transition, it's more and more weakly first order, up to the point where it's becoming second order. And finally above, you don't see a phase transition anymore, you just see this continuous growth of that thing. So what this is predicting, again, in full analogy with what you've learned for first order transition that disappear at high temperatures, disappear through a second order critical point. Okay? And above that, what you have is like, a little bit of criticality, but it disappears and you just have a crossover. Okay, so do you remember how you call the limit of stability of a first order transition point? So you have, a state which is metastable, but finally it's losing its stability. So do you remember the name of that line in some phase diagram where the metastable phase is completely losing its stability? Does anyone remember that? It was in the 4 books I read this morning. It's called spinodal. It means spinodal instability is when the system is losing its stability. So when you begin to be metastable here, it's at the dynamical transition. So the spinodal, in a sense, is that temperature TD, and by construction, the spinodal is going to disappear altogether there. So I should probably use another color and call this a spinodal. Okay. So remember we discussed, I think, two or 3 days ago, when you cross a first order transition, you have some kind of hysteresis. Hysteresis means if I cross the transition, the system can remain stable for a little while up until it jumps by nucleation, as we saw. But if you go too far away here, you cannot maintain hysteresis anymore. The system jumps because it's completely unstable. So the end of the hysteresis is the spinodal. So we had discussed, without thinking about giving it a name before, it's when metastability no longer exists, and if you go there, the system immediately goes to the other phase. So in between the first order transition and the spinodal, in a sense, this is where you have this nucleation that we have discussed 3 days ago. Just a recap of things. So you've learned those things in a simpler context. They just reappear naturally in the context of the random first order transition for the reasons that we have been discussing. So all the physics of, a first order transition sort of applies directly to this extended phase diagram. And so 2 cool things happen with the epsilon. That's why I wanted to mention it. Hopefully I'll be able to come back. The first thing we said is that when you do an experiment or a simulation, there is so much you can do here. You can go up or down to certain temperature, and then you need to stop your experiments or your simulations because, it's taking too long. The system falls out of equilibrium. So there is a certain temperature which is your limit below which measurements can't be done anymore. So the cool thing about this epsilon, so we say it's really difficult to go, close enough to the Kurtzman transition to see it. The cool thing about this epsilon is that if you now increase that epsilon, you can perhaps see the first order transition that I've just described here without having to get there to see the first order transition. And I'll be trying to explain you to this that it's been done in computer simulations at least. So that is, even though you cannot directly access to this guy, hints that this guy exists are very strong in the computer simulation. So the hints that TK exists when you only decrease the temperature have been, debated and discussed heavily, correctly. The hints that this is existing, I think, are very strong, and there is no much doubt about it. The second cool thing about it is the emergence of a second-order critical point. So why do we like it? We like it because we like statistical physics, we like critical exponents and universality classes and all that stuff. And that physics is supposed to be applying to this. And one reason I talk so much about the random field Ising model before is that the universality class of that guy is known. It has been, studied theoretically, and by, as the result of the calculation, symmetries and everything can tell you the result. But the random field Ising model that, whose Hamiltonian I have written down in one of the tutorials, has some critical exponent that I have described to you earlier. And the same set of critical exponents are predicted to describe that second-order critical point in that extended phase diagram for supercool liquids. So that's a very strong prediction that comes out of the entire prediction that, again, because this is happening at much higher temperature, can then be directly tested in computer simulations, for instance. So these are 2 good reasons to think about epsilon. It gives you a way to test, this thermodynamic construction in real models with much more, different types of approaches, this way, instead of just cooling the system and trying to extrapolate things all the time. So I write G, but I don't remember what were the previous letters. Okay. So I want to finish before going to the next lecture quickly about finite dimensional effects on RFOT. And I hope I won't take too much time. So you were asking the questions about, I wanted to go to you. You were asking the questions about what happens if in real space I put 2 of these states and they talk to each other. And I think about the fact that, space exists and I can do things with it. And can I at least from the viewpoint of random first order transition theory, you can at least imagine what's going to happen and what's going to survive, what can survive, and what can not survive. Okay? So the first thing, I think it's it's immediately killing the theory, you would say. So infinite dimensions, so in D smaller than infinity. So when you think about, I have special things and I can create interfaces, domains or length scales or whatever, the system cannot have possess long-lived metastable states. Okay. So I'll show you in a minute why, but you should already be realizing that it's a killer. I mean, the first thing I told you about the mean field construction when we started to discuss the thermodynamics is calculation shows that the key feature of mean field glasses is the emergence of a large number of metastable states. So I go to finite dimensions, and the first thing I understand, and those people of course knew it, is that that cannot be true in finite dimensions. Why cannot it be true? So that's a little bit the argument that you were after. So let's suppose that it's true and we prove that it's stupid. Okay? So suppose it's true. And we have this curve, you know, sigma of f, like this. I'm just reminding you what was the results we want to show is stupid. So let's imagine that you start from a system, you know, that has a given free energy, and I call it alpha. So it's one of those pockets in the configuration space. I imagine that my extended system here is in one of the pockets, and I call alpha the pocket alpha, and it has free energy alpha. Okay. So the one thing I can do in real space when I have geometries and interfaces in length scale that I can not do when I have, you know, an infinite dimensional space where all the variables talk to each other in a very strongly correlated manner, I can do the following. So now let me think about another state that I call beta. So this one, so it's a bit small. So because there are so many pockets, one pocket alpha has free energy F alpha, another pocket beta has free energy F beta, and I assume that F beta is smaller. So what can I do then? You know, this is my system. You know, it has free energy alpha. So what can it do to probe these lower free energy states in real space? There is something it can do that it could not do before. And that's the usual thing that we've drawn before several times already. You can create a droplet, because now we have space, and it can fill that droplet with the state beta. And then you can think about, okay, do you win something or do you lose something, or what's the competition? So that's the competition that we have discussed several times. So if you do that competition and you say, is it favorable for the system that started in alpha to go into that nucleation droplet things? And so again, if you compute the free energy cost of creating that droplet, you know what's going to happen. You'll have two terms. So one will be, you know, in the volume of the droplet of radius r, say, so that would be 2r. So I just don't put the pi prefactors or whatever. In the volume of the droplet, you're going to replace alpha by beta. So you will gain something because F beta is smaller than F alpha. So you go to a lower state. And of course, you have to pay something. You have to pay that alpha and beta are different states. You have to pay some kind of interfacial energy. And I just put D minus 1. So that's where D matters. So when D is not infinity, D and D minus 1 are different. So those two guys are different, as you know very well. And you know that at short r, the r to the d minus 1 wins. So you have a cost. It's difficult to start and create that small bubble. But if r is large enough, the volume term r to the d is going to win. And finally, you're going to decrease the energy. And if you draw that delta f thing versus r, you know that it's going to look like this as usual. So why is it key to have space? It's key because the barrier that you have to cross here, it knows about f alpha minus f beta, that's a finite number, and it knows about the surface tension, and it's a finite length, okay? So that's the critical radius. It's finite, it's not, going to infinity. So the barrier that I have to cross to go to the state beta, it's finite. So the time it's going to take to go there and cross that barrier is finite at finite temperature, meaning I started by assuming that I was in this pocket alpha forever, stuck there, which is the mean field, the picture that we have been discussing over the last 2 days. As I'm telling you in real space, the lifetime of alpha is finite because I can go to beta, and if I can go to beta, of course, I can go to gamma or whatever. So I'm dead. There is no such thing as long-lived metastable states in finite dimensions because the barriers become finite immediately as soon as d is smaller than infinity. Dead. So the entire construction with that sigma of f, it cannot be defined away from these mean field calculations, away from these fully connected models. So everything that I've told you about this entire construction that was clean, nice, and looking like the textbook phase transitions, as soon as d is smaller than infinity, even if it's 200, it's dead, okay? So that's cool. It's a nice construction that seems to be extremely fragile, actually. So that's the first very strong statement in smaller than, in finite dimensions that sigma of f cannot exist. So another consequence of that thing is, remember when we said we call the system, we look at the dynamics, and we lose ergodicity at the first of these two transitions, the dynamic transitions, because we say in between TD and TK, we are stuck forever in these metastable states. I've just shown you that it cannot be true for a finite dimensional system. It means the loss of ergodicity as you cross TD that was so cleanly computed from these dynamic mean field equations, it cannot exist anymore. That means the dynamic transition at TD, where we saw that the relaxation time was predicted to diverge as a power law, it cannot exist either for the same reason. Because the reason it exists is this, and I just told you it cannot be true. Okay, so it means this has some good and some bad you should notice, because I've told you, well, we predict from mean field a power law divergence, and this is not observed in experiment, that power law. Instead, we discuss the exponential and thermally activated law for the relaxation time. But at least it's good because that's the good side of it. If that transition doesn't exist, at least you already know that the prediction that was wrong is, anyway, not describing the experiment, and there is the hope that you can replace it by something, because even self-consistently, you can imagine that it cannot be the case that the relaxation time is going to diverge there. It can only diverge later if it does, if anything survives. So that's the good thing. The bad thing is that all the nice calculations that we discussed, you can do the P-spin model in aging, in shear, in that, and compute everything. Then it has to be taken with a pinch of salt, because when you're going to apply this to real systems, these transitions, strictly speaking, cannot exist at all. And so people are, I think, still debating whether it's totally destroyed and it's becoming totally useless, or whether it's surviving as a strong enough crossover that it can control the physics a little bit, and then theory then can be used to fit some experiments. And so many experiments have been used with such kinds of theory, recalling usually at the end of the papers that, we know it's a crossover, but at least the predictions can be used to fit the data. So let's be a bit more constructive compared to the restriction I've just done to the mean field calculation. And this is one thing I think which is important in the discussion that we say. And this is again trying to answer your question about real space. And point to set length scale exists. Okay, so we say the system as a whole cannot sustain this long-lived metastable state. So let's see whether locally we can define something like metastable state. So let me explain what we do in practice. We do it, I explain how to compute things, and then at the end we stop and I say, well, this is what it means. Okay, so let me be a bit more pragmatic to get started. It's going to look weird, I can tell you, but believe me, it's going to be useful at the end. Okay. So we start, as for the Franz-Parisi potential, we say, let's draw one of those reference configuration from the Boltzmann distribution. So it starts like the, pairs of the clone or the replica calculation, if you will. So this is a reference configuration at equilibrium. And indeed, the construction I want to do is a way to rephrase the mean field construction with these clone copies that, stay together or don't stay together. But now thinking about real space effects that are killing the previous construction. So what can survive? What can survive is the following. So this is my reference configuration. Okay, I give you the position of all the particles, and I call R0 the reference configuration. So it's a very large system. And now this is the thought experiment that we want to do. So we want to consider now a finite volume of that reference configuration. And as usual, I will call R the radius of this finite volume. So step 2, you define a cavity somewhere in your system. And we think about space now, what can happen. Okay, so that's step 2. You define a cavity. Okay, 1. Cavity of radius R. Okay, and we will, of course, play the game of changing the cavity size and see how it affects the system. So the key thing that now we are going to do is we freeze the particle outside the cavity. Okay, so we freeze the position of the particles outside the cavity. Okay, and we do the thermodynamics of the rest. So that's how it was presented initially. What I'm really doing is I'm introducing here the second copy of the system that I usually call Rn. And what I was doing in the Franz-Parisi potential, I was comparing those two configurations, and I was looking at the overlap between these pairs of configurations, and then we computed the free energy associated to the fluctuations of the global overlap between these two guys. Now I do almost the same thing, but I'm constraining the fluctuations of this guy. I'm saying the overlap in the second configuration with the reference, it's 1, and that's the only region that I'm studying, okay? So what I'm really forcing, I'm forcing by this freezing protocol, I'm forcing the overlap between the second configuration and the first one to be 1 outside of the cavity, because I'm freezing the particles outside. And the particles inside, they can do whatever they like. So Q inside the cavity, it can fluctuate because I'm doing thermal fluctuations inside the cavity. So what I really want to do is, instead of letting Q evolve by itself for the entire system, which we just said leads to inconsistencies, now we are looking at fluctuations of Q in a small finite region of space, and we do the entire construction again, but now for a system of size R with the constraints that Q is equal to 1. And that's what we want to do. And the hope is, at least within this constrained construction, something like this phase transition we are going to reappear. Okay? That's one way to think about it, thinking about the Franz-Parisi potential, but with this additional constraint. I think I now can finally answer your question about I put 2 pieces of the material. That construction actually it's been used in mathematical description of phase transitions in general, and the rationale is like this. Imagine that you have, again, a system that is paramagnetic and can become plus or minus magnetization below the critical points of the Ising model. So the system has to choose whether it's going to be plus or minus, and one way to impose the plus or the minus in the Ising model would say, I'm looking at the phase behavior of the system, imposing at the boundary that the phase at the boundary is in one of the equilibrium states. So if I impose the plus and I let the system decide in which phase it's going to go, well, by construction, it's going to end up into the plus. If I just look at the system, it could end up into the plus or the minus. So the analogy with us here is I said instead of having two metastable states, I have exponential n sigma metastable states. So the system can fall into each one of them. So now what I'm doing by that construction, I'm imposing one of the states at the boundary, and I'm checking whether, imposing something at the boundary is going to propagate and impose the same state outside in the unconstrained system. And that construction is really what people do and think when they think about phase transitions, even outside of the field of the class transition. So you can imagine intuitively what's going to happen, I think. Imagine that you constrain the system so much that you leave just 3 or 4 particles in the middle. The particles there will be so much constraints, but what's happening at the boundary that they will stay there forever, and essentially they will not be able to move at all. In the opposite limit, we already know the result. If the cavity size is super large, we know that the system is going to start and explore this diversity of geometric packings that it can explore. So intuitively, what this construction is about trying to vary R between the point where the system is nearly free and then it's just one of these liquids, down to the point where the constraint is so strong at the boundary that the order inside is going to propagate inside. And so that's the essence of that construction. And how do you relate this to the quantities we've discussed before? It's going to be by an argument like this, again, which we use extremely frequently in glass physics. And so the final part of the argument goes like this. So imagine that the cavity goes and starts to explore the diversity of packings that it can explore. So what's the cost? Again, what's the competition and what can the system do? So let me write it once more, and then we discuss it again. Okay, so if the particles inside the cavity, they want to explore different states, what do they gain? They gain the free energy of exploring different states, and we see that the free energy, remember that the free energy difference between localized or delocalized in the Franz-Parisi potential was this entropic term, the configurational entropy. What do you lose? As usual, you lose that the system now is not happy at the boundary, and you have to pay again some kind of surface tension. So that's the competition I was saying. If the cavity size is small, this term wins. If the cavity size is large, this term wins. And as usual, I've drawn that picture so many times these days that it's again the same type of competition. So when the surface term is winning, it means it's not favorable to go outside, so the particles stay close to the initial configuration, and then the overlap will be close to 1. Okay. When the diameter or the radius of the cavity is large, it's going to become extremely favorable to the system to explore this diversity of state, this configurational entropy, and then the system will fall into a regime where Q is equal to 0. And the boundary between those two things are when, these things roughly are equal. And so the crossover length, and finally you have the explanation for that name. It's called the point-2 set correlation length, and then it's the competition between sigma, roughly, and that T sigma of T term. Okay? So what did we do? What did we say? Something relatively simple. We started by saying if I have a large system, a metastable state cannot survive for long, and if I start in a given configuration, I'm going to explore in a finite time other configurations. Now, I've told you if you do the same thing, but in a constrained cavity here, if the cavity size is smaller than that length, the system is going to stay there forever. So it's going to be stable for an infinitely long time because you're not going to explore other configurations. So at least if you confine the system on the length scale that's smaller than the point to set, then metastable state with an infinite lifetime exists. Okay? So when R is smaller than R star, or C point to set, so on the finite length scale now, the idea of metastable state can be defined. And that's the whole point of the construction. So metastable states exist. And on length scales larger than the point to set, that were point 1 and 2 of my discussion today, the construction based on metastable state breaks down, and the mean field construction breaks down. So that's the idea that maybe when you, sorry, that's one thing. The second thing is not the connection between the configurational entropy and the length. So it means the length, point to set, is proportional to 1 over T sigma. So if the configurational entropy in practice goes down rather quickly, if it does, then that length is going to become large as you approach the Kaufman transition. Okay? So it means if you're close enough to this Kaufman transition where you have very few of these packings left, the idea is that then the system, at least on the length scale that is really diverging as you approach the glass transition, locally it's looking like one of these mean field models with all the physics that we have discussed so far. And it's only at larger length scales that the whole construction breaks down. So that's the bottom line of this construction, and that's why people have thought about it. It means, okay, in finite dimensions, strictly speaking, it seems to be breaking down, but if I introduce that length scale, then at least on the finite length scale, there is a hope that the mean field construction can be useful. So why can it be useful? For many things that I have no time to discuss. But one reason why people think it may be interesting and useful is the connection to the dynamics, okay, that we want to re-establish. So is there a connection to the dynamics? And how does such a system relax in finite dimensions? So we saw in infinite dimensions, you lose ergodicity at TD. We've proved in 5 minutes that that cannot be true in finite dimensions. In finite dimension, instead, the system is mean field-like on the finite length Xi point to set. So what people have argued is like this. They have argued that, in between that TD crossover and that TK, instead of thinking the system is totally non-ergodic in one of the pockets of configuration space, I should think of the system again in real space as being like composed of, sort of domains. And I have this growing correlation length, and at the local scale, for length scale smaller than Xi point to set, the system is really believing its mean field. So locally, it's really, totally frozen. But that length scale is finite, so the barrier to cross to escape from that state will remain finite. And so people have argued for a long time that maybe, the typical time it would take to cross that barrier, and I should probably use the exponential, would be, by this type of activated scaling. Okay, so on length scale smaller than Xi point to set, I'm totally frozen, I said. So you're going to cross barriers related to the size of these domains. And so people have postulated that, it's a way of thinking of the dynamics of these correlated domains is saying, well, I need to move everybody together, at least on this volume, in order to relax. It's going to take me some time, and again, by analogies with all the disordered systems and the activated processes that we have been describing in the first 3 days, people have thought about a connection between this correlation length that grows and the growth of the relaxation time. And so why is it, first of all, popular or anything? It means that the log of 2 alpha, then it's the Xi point to set to the Psi divided by T. And remember that the point to set is related to the configurational entropy. That means it's going to be 1 over T sigma to the Psi or something like this. So that's making the connection that we have been also discussing several times. The idea that if you have fewer states, smaller entropy, then the correlation time should be larger because it's getting more and more difficult to find different states. So that, thing has been discussed several times, and I've told you, I think 2 lectures ago, it has even a name. It's looking like this Adam-Gibbs relation that goes by to 1965. So in those years, nothing of the mean field construction was known. The point-to-set length wasn't known, but still these guys had connected to alpha to the configurational entropy. This entire construction that I've shown you, yesterday and today, it's a way to get to similar expressions, similar physics in a much more precise manner. So you can think of this as a way to justify, many years, decades later, why the Adam-Gibbs relation may have something to say about the dynamics of supercooled liquids. So that's one reason why you want to express this. And the second reason is much more basic. So remember what we said. In terms of the temperature, we had that TV, that decay, and the mean field model was having this power law divergence like this. Okay, so that's the mean field dynamics. So the minute you think that the dimensions of space is finite, or that length scales and geometry matters, we say that thing has to disappear in finite D, and that law where the system has a power law divergence, it has to be wrong, incorrect. It cannot exist in mean field. So you do more thinking about what can it do then. It can grow these domains related to the configurational entropy, and those domains may or may not explain the dynamics, but at least you can argue that the real law is really that thing, the exponential xi to the psi divided by t. And that one is going to diverge when the configurational entropy goes to 0. So it's giving you a way to at least wave your hands and argue that the real type of law, it's an exponential with an activation energy that grows, and that grows by something which is the configurational entropy. So it has all the right ingredients to potentially explain the physics of supercooled liquids. It hasn't been proven that this is all true, and people have worked hard to try and prove this. It's not known, we don't know, but at least it's one possible way of explaining the experimental data that I've shown you in the first lectures, and it's very consistent, and many pieces of this can be shown to be there in real supercooled liquids. I think you had a question like half an hour ago that I discarded. So if you want to ask it, it's now because I'm going to change topic later. So I'm sorry for that, I forgot.
Why it's Xi power 4? The activation
sorry?
energy is Xi power 4.
Ah, sorry, it's not 4, it's psi. It's my handwriting.
Oh, 5, okay.
Psi. In LaTeX.
Okay, and
it's an easy one, thank you.
And the previous question was this, that you did Legendre transformation with epsilon q.
Yes.
So in computer simulation, you said yesterday that you can do bias simulation to explore those.
Yes.
So how do you do that in
Tomorrow,
simulation?
I will explain tomorrow normally.
I see.
So that's for tomorrow. So I leave the question for tomorrow. I hope you can at least listen to it.
Okay, thank you.
Okay. So I took a bit more time than expected, so I'm going to try and do that thing slightly faster than anticipated. So I'm going to leave the realm of mean field theory to go towards finite dimensions in steps. And so the first step I'd like to share with you is this idea that in between the experiments, or the colloidal or the molecular experiments, the mean field theory that we have been describing today, which is a bit involved and complicated and whose validity you don't know, And then at the end, which we'll do tomorrow, and many of you are doing this, are the computer simulations of the Earth lattice particle models in 3 dimensions. There is a whole class of models which are in between. We like them because we like to do statistical physics. So many models in statistical physics are simplifications of the reality, lattice models. They are useful for many reasons. Usually, if you simplify the problem into a lattice problem, but you keep the main ingredients, you can get the right answer. Sometimes it's much easier to simulate lattice models. You can easily, change the space dimensions, the geometry of your lattice, whatever. And that can be much simpler to simulate, and maybe it's much easier to understand the physics of these models. And then you can decide whether they look like the real experiments or the atomistic simulations. But it's an intermediate way that I think in a school dedicated to statistical physics could deserve 45 minutes. I'm going to show you that there is like a zoo of lattice models that people have used over the years to try and see whether either you can test in those models, theoretical predictions, or devise lattice models that do have all the characteristics of realistic experimental supercooled liquid, and can be used perhaps to say, well, I have a lattice model, it's showing all the right phenomenology, but the origin of the slowing down of the dynamics in this model has nothing to do with it. So you learn that other mechanisms compared to the ones that we have been discussing over the last 2 days also exist. And then when you go back to experiments and simulations, you can ask yourself, do I see one mechanism or I see the other one? And can I discriminate, and how different are they? And it's, I think, making the discussion of analysis of simulations, for instance, or experiments, much richer, because then you have different ways of thinking of the same, say, movie or measurements you're making in your simulations. Okay. So I'm going to try and be a bit faster than expected. And so there is a family of models that grow in, the same period that I was mentioning. So Kotzmann was 1948, and then Adam Gibbs 65 at the time. In those years, people wanted to understand a little bit about glass physics. So I won't spend time on this one. I'm going to use just simple ideas. So there is one model, and it's just one of many models, but this one we like. It's thinking about, instead of complicated correlations, entropy, I'm going to think in terms of the questions we have been discussing so far. What about defects in those structures? And can there be defects, and can they be ruling the dynamics and the statics of this model? So Glarom has developed one of these models. I'm going just to sketch the model. So he solved this model in 1D. So it's a 1D model with defects. And so his idea was to say, let's postulate that the dynamics is controlled by some kind of vacancies. He has no idea what the vacancies could be, but I postulate vacancies exist. So these are, like a dilute gas of vacancies, as usual, okay? And so what he wanted to say is describe the impact of these diffusing vacancies, few of them, on, I have one molecule here inside my liquid, and the liquid is full of molecules, but I have these rare defects that exist and diffuse on the lattice. So essentially what he was doing, he was saying, I have these rare gas of vacancies, they diffuse on this, and when the vacancy is finally diffusing to that particular tracer molecules that I'm looking at, it's making it rotate very quickly. So in this view, the molecules are completely stuck because you have all your neighbors, but then you have vacancies that come, and when they come, they hit you and you can relax. That's the mechanism. Sorry? I cannot hear you, sorry.
Can you please repeat the model? The model that you used.
Can you please repeat the model once?
Okay. So I imagine that my liquid is full of molecules. It's very dense, very packed. If I look at one molecule alone, it cannot do anything because just like you're surrounded by your two guys, you cannot move, okay? That's postulate number one. I'm looking at one of these molecules, it's stuck for very long times. It cannot easily rotate. Okay? So now I postulate the existence of like a family of defects. I don't know what they are, but they are very dilute. Like there is one chair here which is empty, just one. Okay? So it means the guy sitting next to the empty chair can move very easily, but just him can move. So he can relax very quickly. So it means if I'm getting close to a vacancy, I can do something. So he can change chair, and he has liberty of freedom to move quite easily. You cannot. But when he moves, then the guy next to him will have an empty chair. So he can start and do something himself. So if we imagine that we have vacancies that go throughout the room, one by one, you'll be able to do something. At the end of the travel of the vacancies, I have relaxed all of you. You're all happy. You have done something once. And this is the mechanism that Glarom described there. So why is it, leading to interesting glassy dynamics in one word? And I wanted to do the calculation, but I want, if those defects are, extremely rare, most of the time you're not sitting next to an empty chair. You're sitting next to two guys. And you have to wait up until the vacancy diffuses to get hit and finally relax. Number one, dynamics is slow because very few vacancies. So the dilute here is really key. The second thing that people liked at the time, and that's related to the lecture that you've been hearing about, random walks and, distributions. If you have rare, again, dilute gas, the distance to the next empty chair will be short for him, but very long for Pinaki, for instance. So the time scale for this guy and for Pinaki will be widely different because you have all these, properties of random walkers that if you want to be hit by a target, as we heard yesterday, that immediately leads to broad distribution because the distance to the target varies. And even in 1D, it's awful because, the time it takes to go somewhere usually is power law distributed, for instance. Okay? So this is why the model of Glarom, when he does all the calculation based on random walk calculations similar to the other lectures, it leads to slow dynamics related to the absolute concentration and broad distribution of relaxation time, so wide diversity of relaxation time. So you have all the physics of dynamic heterogeneity and slow dynamics in a model where you have just random walkers on a 1D lattice. And that's it. Here you have no thermodynamic, no entropy, no nothing. You control that stupidly, it looks stupid at first sight, but if you work out the kinetics of that model, it has many, many good ingredients actually compared to what I've told you about experimental systems.
So would it be similar to symmetric simulation circumstance with high density?
I was expecting that question. I was looking at you and I said he's going to ask a question like this. So I started to think about it, but then I haven't converged. But I think it's going to be, and let me again move forwards and I'll go into models that look very much like the types of lattice model with constraints. So here, I don't even have particle, I just have diffusive defects. With no, at least the defect can diffuse easily with no constraint. I'll go to the type of model you like. Okay. So that's model one, that was the 60s, and then came like a better version of the same idea. So I'm going to describe the Fredrickson-Andersen. So I just write it capital E. Okay. So there is a guy in the glass literature that has developed many models for glasses. He's called Andersen with an E at the end. Yesterday we had the tap equation with Andersen with the O. And so if you look at citations to the poor Andersen, many times it has been switched to Andersen, poor guy, okay? But Andersen exists, and the Cobb Andersen that like half of the room knows, it's really Andersen and not Andersen. So be careful in your citations. He's retired, so he cannot care anymore. But, so it all started in '84, so it's 20 years or 25 years later after Glarom. And the assumptions are essentially the same as Glarom, but put in a statistical mechanics context. And so let me just write down the Hamiltonian they have. Okay, so he starts by assuming similarly that there is a dilute gas of vacancies, and instead of thinking of the molecules, Fredrickson-Andersen say, I don't care about the molecules, I'm going to care about the vacancies themselves. So I describe a rare gas of dilute vacancies. So the vacancies are so dilute that they don't interact. So that's the simplest Hamiltonian you can have. So that variable is like 1 and 0. 1 if you're a defect, and 0 if you're not. And being a defect costs you an energy scale 1. Okay? So if you do the thermodynamics of the ideal gas, you can very quickly understand that the average concentration, that will be C of T, with this non-interacting Hamiltonian is going to be 1 plus 1 over T. So the 1 here is the same one that I have put in front. I could put a J, but I don't care. So it means at low temperature, it's exponentially suppressed as you decrease the temperature. So exponentially suppressed means at low temperature, very few of the sites will be 1, and most of the sites will be 0. And this is decreasing very quickly as you decrease the temperature, exponentially fast. It's Arrhenius. And so this is what Fredriksson and Andersen did. They took this idea of defects, and they say, we look at the defects, and we make an Ising model of it. And I think the title of this paper is like a kinetic Ising model for the glass transition. So it's transforming this idea into an Ising-like version of the physics. So now you have to give the defect some kind of dynamics, and this is where comes the second idea, which is again already done in Glarum. So if I'm thinking, I take a random site here, I've told you the only moment I can relax is when I'm close to a vacancy. So 2% here can relax. So this is what they try to incorporate in some detailed kinetic rules. So they say, a given site I can make a transition between 0 and the state 1 with some rate, okay, something like this. And so what's the probability to get excited? So remember that we need to satisfy that rule. So one thing that you need to have is that the probability to get excited must be small in order to conserve the thermodynamics, okay? And so the reverse transition by something called detailed balance has to be like this. So if you put these kinetic rules, at least, if you do simulations where the probability to go up and down satisfy those rules, you'll satisfy detailed balance with this Hamiltonian. You'll get to this rare gas of dilute defects. I haven't put any interesting physics yet. It's just spins that flip independently. So we need to introduce one more ingredient, and this is what they did. And they introduced a function I here, which is the same for the up and the down transition, such that if I take the ratio of doing this and the ratio of doing that, the Fi disappear, and I still satisfy detailed balance with respect to this Hamiltonian. So the fact that it's at the top and the bottom is to be in equilibrium with this Hamiltonian, first thing. The second thing is, what do I take as a clever choice for the function Fi? That's where they were, I think, very clever. So they defined something like this, and they said, we'll make that function Fi, we'll make it equal to 0 for many transitions. That is, we are going to put constraints on what the system can do, okay? And of course, that's just the generic idea. So I'm going to kill some of the dynamics to make it slow and constrained, first thing. And so now I have to specify how to do this in practice and just define like constructively a model. Okay. So they have defined a family of models. So I'm trying to make it just a little bit generic, but let me call it like this. F and D. There is a family of F, D, F, A model. So it's a bit complicated. So you have two parameters, F and D, and F and A stand for Fredriksson and Andersen model. Okay, so there is a whole family which depends on two parameters. So one parameter is easy. This is just the space dimension. Okay, so you can be in 1, 2, 3, 4 dimensions. So that's defining the lattice on which those spins are living. And the dimensionality, of course, matters into the physics. So that's leaving us this just one parameter here. So I'm going to describe it with a cartoon. Okay. No, I don't like this one. So let me draw the two-dimensional lattice. I just specify, say, Okay, so I'm going to look at the F2 FA model. So I'm in 2 dimensions, and I'm thinking, I'm one of the spins. So this is, lattice I, and I'm trying to think what can I do when I'm sitting at lattice I. So I have to look at my nearest neighbors. So these are my 4 nearest neighbors. 1 neighbor, 3 neighbors. So I have 4 nearest neighbors. Okay, and so the rule that's the one which is wet. Okay, that's the rule that they have adopted. So they say Fi is 1 if the number of up spins among in my neighbors is larger or equal to F. Okay, and it's 0 otherwise. Okay, and one model that they have studied in this paper and in a series of 3 very nice papers following that, they have studied then the two FA model extensively because it was showing them beautiful glassy dynamics with a non-interacting Hamiltonian that they were very happy. So what does it mean? So the 2 here is the space dimensions, square lattice, no problem. So what does F equals 2 means? It means if I want to decide whether that spin in the middle can flip one way or the other, I need to look at my neighbors. So I have 4 neighbors. And if I have less than 2 of these guys that are up, I'm totally frozen. That rate is 0, that rate is 0, so I cannot get excited, I cannot de-excite, I cannot do anything. I'm frozen in my state, okay? Unless at least 2 of these 4 guys are themselves up spins, and that's the key idea. It means, remember, at low temperatures, very few sites will be excited, very, very few. So if I take, one lattice at random, typically it's going to be very far from a vacancy, from an upspin, from a defect. If I'm far from a defect, I have 0 of my neighbors that can help me. I'm frozen forever. I cannot do anything, okay? I'm constrained. Now these vacancies are going to move. One guy gets excited. It's not enough. I need 2 to make something. That means if I want to do anything, go up or down, and I want that function to be non-zero, 1, then I need to wait up until 2 up spins come, and finally they go there, and I can start moving. Okay? So this is the very strong constraint that they put on the dynamics. They say, I have very few up spins, very few defects, and I cannot move up until I have 2 defects next to me, and then I can start to do something. And that's the idea, again, of Glahome saying, I cannot do anything unless I have enough space to do something. That means if I have 1 chair empty, I can do a little bit, but you're still stuck. You cannot go to the bathroom. It means I need to have many, many chairs, and then I can go away, and I can go and escape completely. That's the same idea. I need to have enough excitations next to me to be able to do something. And that's the model. And of course, you can do any F, any D that you like. And if F is, if that function is always 1, then you have the unconstrained dynamics. If that function is very large and you're asking for a very large number of defects to start doing something, is going to be very, very constrained, because having 4 defects will be very, very rare at low temperatures. So by playing with these parameters, you can have very constrained, a bit less constrained, or totally unconstrained models, and you have a zoo of, Fredrickson or Anderson models with different types of physical behavior. But the key idea is very few defects. There are so few that I can postulate they don't interact between themselves. So the statistics of these defects is completely easy to compute. I forget about my molecules. I forget about the entropy, the states, the packings, the density, everything. I think about the defects. And I need defects to get starting something. So that's the key idea of these kineticizing models. It's going to be tough to finish. So I'm making choices as I go among the different models. I want to answer his question maybe. So here you have spins that can go up and down. That is, an excitation can disappear, can be created. There is nothing like a conservation, nothing like a density being conserved. I think the question was about lattice gases. So I'm going to show you some models with conserved density. So I'm going to show you lattice gas models with the same physics, okay? So lattice gas models that have kinetic constraints, trivial thermodynamics, and do lead to these constraint dynamics. Okay, so now I'm thinking that my variable Ni on the lattice, which is 0 and 1, I'm going towards 0. So I have a lattice, I have, instead of thinking of them of spins, I can think this is an occupation number, okay? And then I'm switching to the type of problems that you were thinking about. I have particles on the lattice now, and each lattice site can be occupied by at most one particle. So it is empty or it's a vacancies now. Okay. Okay, so that's again the lattice. And now I need to think about particles. Okay, so I have, say, one particle here. So that particular site now is occupied by a particle. Okay, I'm saying that the only thing that the particles do, they exist on the lattice, but there is no, apart from the hardcore exclusion, no attraction, no energy scale with the interactions. So it's just the type of model that you were asking before. Volume exclusion, and then I have to give kinetic rules for what the particles can do. Okay, so a particle can hop, by one lattice site. So for instance, do something like this. So it can site to, say, this site. So what are the conditions to allow for this particle to jump to that site with a question mark? So the site needs to be empty, okay? Otherwise, if someone is there, then I cannot jump. That's the hardcore volume exclusion. And that's where I think, again, the idea of I need enough vacancies to make a move, and it's the number of neighbors before and after the move is smaller or equal to m. Okay? So this is the kinetic constraints. It means in order to be able to jump, of course, I need to jump to a site that's not occupied. So let's assume that this site is really empty. So in principle, I can do it in the type of model that he was asking about. You can always do it. But here we put an additional constraint. We are saying if among your neighbors here, again, you have your 4 neighbors. If among your neighbors you don't have vacancies in large enough numbers, if you don't have enough vacancies, you can't do the jump. Okay? So it means if it's occupied, and empty, I refuse the jump. So that's the constraint. It means, again, instead of thinking of defects, in order to be able to make some moves, I need some space. That's my chair analogy. In order to make jumps, I need to have empty chairs surrounding me before and after the move. So I need empty chairs also after the move to satisfy detail balance. So the idea is again the same. If I have lots of volume surrounding me, I'm able to make a move. If I'm completely stuck, I cannot move. That's always the same idea, and it's the idea that now vacancies are, helping you making the moves. When the density of the system is large, vacancies will be very rare. So sites with empty space nearby will be very rare. So the sites that are not blocked by the kinetic constraints will be rare. The dynamics will be slow, and actually the lattice gases and the FA models essentially display the same physics. It's just a lattice gas version that I explained especially for you, so it's my special present. There are, again, tons and tons of lattice gases, which I wanted to describe in some sense, but I think I don't have time. So this morning we added to the website 2 things, a copy of the notes, so the ones on my, so you can take a look at the different models on my notes. They're available on the website, at least, one of them. The second thing I did, I gave also a list of simple enough references, and I gave a reference to a book chapter which is called Kinetically Constrained Models. It's a book chapter written by Peter Solich, Juan Pegaran, and Cristina Toninelli. It's available on arXiv. I gave the link or the arXiv reference, and it's about 20 pages, and it's describing essentially in 20 pages what I'm going to spend 10 minutes describing. But it's very easy to read, and it's not very technical. So I think it's a nice introduction to this family of kinetically constrained models. So I had a few pages about the physics of these lattice glass kinetically constrained models. I'll do just a little bit. The physics is really, for the simplest one of them, it's really, like the physics of Glarum, but now you can compute because you have a microscopic model with well-defined rules. You can do computer simulation. It's just you don't think about molecules. So the one-dimensional FA model is the simplest case of a model where you can understand everything super easily what's happening. Okay, so let's do it as a cartoon. So I have an upspin, and I'm just not drawing the spins that are not excited. So most of the spins are 0. I don't draw M. And then you have, from time to time, with that very small concentration, you have a spin that's up. And remember the kinetic rule. If I'm not sitting close to one of the defects, I cannot do anything. So this guy cannot do anything. This guy cannot do anything. And this guy is sitting next to 2 down spins. So this guy is frozen as well. So the only 2 guys that can do something are this one sitting next to this one, or this one which is sitting next to this one. So only 2 sides in this chain of empty sides with one defect. Only 2 sides can move, either the left one or the right one. So if I imagine, what would be a trajectory for that system, the only thing that can happen, so nothing happens for very long times, perhaps, and one possibility is that this is happening. Okay? That finally this side decides to jump with a rate. Remember that the probability to do this, so the rate is proportional to C of t, which is very small. So it's happening infrequently. So most of the time, nothing happens, and suddenly, with a small probability, you can make one jump. Okay? So let's think of this new state. So now, what are the sides that can do something? So this side can do something. It's sitting next to this one. That side can do something. It's sitting next to an excitation. That one can also do something. It's sitting next to. And that side is also sitting, and the rest are still dead. So now I have choices. 4 sides can do something, so I can do many things. I could do a third excitation, or I could make one of the 2 excitations disappear, or I could create a third excitation on the right. And everything can happen, but with a large probability, typically the next step will be nothing, nothing, nothing. And then this guy survives, and this guy disappears. So the rate for one guy to de-excite is 1 minus t. Okay? And C being very small, 1 minus C is very large. So as soon as you have 2 excitation, very quickly one of them is going to disappear. So if this one disappears, you're back to the previous, so it's boring. If the other one disappears, then it starts to be a little bit interesting because the excitation that was there eventually started to diffuse. Okay? And so the diffusion constant is limited by that rate, and it means you have defects that diffuse in the lattice with a diffusion constant proportional to that C of t, which is exponential minus 1 over t. So that's the cool thing about these kinetic rules. Very few defects, and those defects, they start to diffuse, but they start to diffuse at a rate that's already changing very quickly as you decrease the temperature. So you have very few defects, and they're very slow, and you have a population of them and a distribution of length scales between them. So I unzoom this space-time thing, and I'm just drawing the space, and I'm drawing the time. And so what I've told you is if I start with one defect and I look at what it's going to do, it's going to diffuse essentially. So I'm drawing a picture just unlike, not unlike yours in your picture. It's just a random walk with a diffusion constant d of t. So So that's typically what's happening. Then we haven't said, but imagine that I create a third excitation here, for instance, from time to time. It's going to be less complicated. Then I can de-excite in the middle. I can branch like this. So with some probability, the random mode can do some kind of branching. So when I create 3, I make disappear the one in the middle, and those 2 can diffuse apart. This is a branching thing, okay? So you have diffusion, then you have some branching events. And of course, if you have then 2 vacancies or 2 defects that appear, finally one of them can disappear. And so you could have, if you have another defect that diffuses around, you could have some kind of annihilation. Okay. And that's the physics of the simplest of this A-phase model. You have vacancies that diffuse very slowly. When they meet, they can annihilate, and when they are alone, they can branch and create this structure in space-time. Okay? And so if you are one of the sites in between and far from any vacancy, for very long times, you do nothing, you do nothing, you do nothing, and that vacancy is going to come next to you, and finally you can relax. Okay? So it means the time it takes for, typically, for one guy to be hit by a defect is going to set the relaxation time of the system. Okay. And the other quantity that I think is interesting is the typical distance between those defects will depend strongly on temperature, because remember that the concentration of the guys decreases. So the typical distance between them, that length here, it's controlled by the temperature. It's 1 over c of t, and it's exponential 1 over. So it is diverging exponentially fast with the temperature. So you see that when you decrease the temperature, the typical distance between defects is growing. The time it takes for this guy to diffuse over a larger distance grows for 2 reasons. The length is larger, and the rate at which they move is larger. So it's going to be going. It's going to be very slow at very low temperatures. So you do all those calculations, and then you realize that for that particular system, the time it takes to relax the system on average is exponential 3 divided by t. So the 3 is the interesting bit. Remember, we just put the 1 in the Hamiltonian, the 1 in the statics, but the 3 is emerging by the diffusive dynamics I've just described to you. This, and if you look again, as I say, to the distribution of time and space, you have strong dynamic heterogeneities, which I don't have time to describe. You have broad distributions, you have large fluctuations. Okay, so you have a whole series of interesting physical properties for this model, and remember, is the simplest of a gigantic family. Okay, so I took the simplest one with this idea of kinetic constraints. I can only move if something is moving nearby. Zero interaction. I look at the glassy dynamics. It 1D for the simplest rule. It's already super complicated and extremely rich. And then, of course, you can go to 2, 3, 4 dimensions. You can make the rules more complicated. You can make lattice gases with different geometries and find behaviors that are similar to this, larger lengths, broader distribution, strong dynamic heterogeneities, and you can change that rule to more complicated, slower, more super Arrhenius rule, for instance. So that's I wanted to describe one, but I will skip it. Model with, I didn't use the word fragile before. So model with super Arrhenius behavior. Exist. Okay, so there is a whole kind of zoo of models. They all have their own, internal rules and dynamics. It's sometimes way more complicated to analyze, by the way, but some of them, of course, can even improve on this and get, interesting predictions for the relaxation time while keeping heterogeneity distributions and physical time correlation functions perfectly fine with the experiments. So that's, I think, a good lesson that I wanted to draw. I went a bit fast, but what do we learn? We learn that by starting from a completely different viewpoint, I'm thinking in terms of rare defects, like Glarom, like Fredrickson-Andersen. I can construct models that are very interesting. They have nice physical properties that are fun to analyze. What time does it take to be hit by a defect? It resembles a little bit the types of questions you were asking. So the distributions are naturally quite broad. And you get very quickly, naturally, properties that if I give you the outcome of computer simulations of a 1D spin model with no interaction, you can confuse them for experimental results, for instance, very easily. And they are very, very, I think, empirically, those models are extremely rich, and you understand everything of the underlying physics. And you've put nothing of the random first-order transition theory ingredients. And now I go to your experiments on colloidal glasses, and you show me something. Is it error 40 or is it rare defects? How do you decide? The outcome at the level of the measurements will be very close, very similar, and yet the mechanisms are strongly very different. So that, I think, is one lesson I wanted to draw for you. So I'll make a few points without explaining too much. I wanted to go to two other families of models. I'll try to spend 5 minutes on each. But a few points that I want to make. So I'm saying models more complicated exist. So in particular, you have models, There is a model that predicts something like this. So it's called the East model that I don't explain, but it's in the note. And this one, for reasons that are going to be clear in 1 second, has been studied to death. Okay? And the reason it has been studied to death is that the predicted relaxation time is something like exponential constant divided by t squared. Okay, that's a law that I think I have described in one of the first 2 days. It was called the Besler law. And so it's clearly stronger than Arrhenius because the effective activation energy is 1 over t. That's what Besler had guessed based on fitting experimental data. And in the East model, this is exactly realized. The second thing that's exactly realized is that the typical length scale that you get in connection to the time scale, so the connection between length and times in relation to this dynamic heterogeneity measurement, it's extremely realistic. Okay, so the types of length scale that you predict, it's extremely realistic. So on the face of it, it's a bit like the P-spin model. You don't know why, but the P-spin model gets all the ingredients right for random first-order transition, starting from an abstract model, but it gives you all the physics that more complicated approaches are giving you. The East model similarly has strange rules. You don't understand why these rules would be better than another one of this big family of kinetically constrained models. Yet you study it, you look at it, you put the numbers, you push, and you see no problem at all. There is no contradiction between the quantitative outcome of this model and the experiment. And there is a group of people, like David Chandler and Juan Pegahan, who have pushed to say, well, all the experiments we know so far, they're all consistent with all the predictions quantitatively of the East model. So it's one of these models where you don't know how to really justify it from first principle, but if you look at it, really it's spectacularly good. And other models, they are less good, okay? In the following sense, like the FA model, it's fine, you understand everything, but at the end of the day, you have a growth which is fast, but it's still Arrhenius, it's not super Arrhenius, so it's not capturing one key things. The other models, sometimes there are two constraints. So there are models, for instance, the Tuto FA model, which is the original model studied by Fredriksson and Andersen. The relaxation time goes like this. It's exponential 1 over t times exponential 1 over t with, prefactors and everywhere. But it's a double exponential. It means the activation energy, instead of being 1 over t or something, it's exploding exponentially, so it's super fast. And you can construct model where it's exponential of an exponential, making the system more and more constraints, for instance. And these systems, then, they are a bit less good because they predict divergences that look a bit too strong. Okay. And finally, maybe I should say it, there even exists model with finite temperature transitions. So there are models with it's a bit at the bottom, but today I think we don't care. Well, this is 1 over t minus td to the gamma. So there are even models with power law divergences at a finite temperature. So, you know, you start from these ideas of kinetic constraints in the rates and a small population of defects, and you can recover a huge variety of behaviors, including ones that look like the mean field models, one that are two constraints, and one that are extremely realistic. Okay, 5 minutes. So I skipped this one. So I skipped one letter, so I'm going to go to and I'm going to confuse you in the last minute. Okay, so I'm going to define a different family of models, and I call them lattice glass models, or they have the flavor of the Fredrickson-Anderson-like. They are models for glasses on the lattice, so lattice glass models. But this time I won't play with the idea of rare defects. I'm going to play with the idea of on the lattice, if I have a particle nearby, it's difficult to move. So this is how these models are constructed, and I'm just repeating the definition of the model. So it's a paper by Biroli and Mézard that started it, and the year is 2002, physical regulators, I guess. So it starts similarly. This is an occupation number. And then I'm trying to think about how to put the constraints that, you know, when I have too many neighbors, it's complicated. So the way that Fredrickson and Anderson and the lattice gas people have used is they say, I cannot move if I don't have enough space. This is, you know, the argument of the empty chair. This is not at all what Biroli and Mézard did. They said, if I don't have enough chairs, it's forbidden. Yeah, so that's the rule. So the rule goes like this. So for each particle on the lattice, okay, so this is site I. So I define a quantity which is Li, which is the number of neighbors. Okay, so I look at the 4 lattice sites surrounding me, for instance, in that case. I count how many particles are among my nearest neighbors. And I'm saying configurations where Li is larger than something that I define, which is the parameter of the model, are completely forbidden. Okay. So it means if L is equal to 3, a configuration where I'm surrounding by 4 particles cannot exist. It doesn't count. I cannot go there, never. It's forbidden by the Hamiltonian. I don't say anything about how I move the particle. I'm saying configurations where the local density is too large cannot exist. I don't have space to squeeze all the particles. And of course, if L is equal to 4, then I can fill the lattice and there is no constraint. But as soon as L is equal to 3 or 2, it means a particle can only be there if at least there is some space surrounding it. Otherwise, that configuration doesn't exist. Okay? So in terms of what you're doing, again, you're not preventing moves if you don't have enough space. You're just saying if the room is full, it's forbidden. You know, there is a law that decides that if you don't have enough space next to you, it's forbidden. I exclude that configuration. So what are these people really doing? They are thinking not in real space, if you want, but they go back to the configuration space. And they say there are regions of configuration space that I exclude. Okay, regions where, you know, some lattice have too many neighbors. They don't exist. Dot configurations don't exist. And you see that at low densities where you can have many vacancies next to you, the system will be. So what you're putting your constraints on the configuration space. And they are not on the kinetics. So it's another way to sort of incorporating the same physics, but it's dramatically different. It's orthogonal completely to the rules of defects and kinetic constraints. But it seems to be capturing the same physical idea that, if you don't like to be surrounded by too many particles, otherwise the system is too constrained. Again, a whole zoo and family of things. And so the one thing that I would like to say about it is that, if you study a d equals 3 or d equals 2 version of that thing, you study the physical dimensions. It's a complicated problem. You cannot, easily solve the statistical mechanics of those things. So what's the physical behavior of that system in finite dimensions? Nobody knows. It's just a model that has slow dynamics. It has dynamic heterogeneity. It is slow. It has broad distributions. It has, all the right physical ingredients. So on the face of it, empirically, it's a very good model for glasses, first of all. But what are the mechanisms? What the thermodynamic is, we cannot compute exactly. There is one limit where the calculations have been done, is when you take this model and you go to mean field. Okay, so people have defined mean field versions of those lattice glass models where the constraints are put in the Hamiltonian, if you wish, and they have done essentially some kind of better lattice approximation. So you go to one of these mean field limits. Instead of being spherical of large dimensions, you do like the beta lattice. It's one way to do mean field. And if you take this model and you study it in some mean field limit, what is the physical behavior that emerges? You take that model with the complicated Hamiltonian with the constraints, you put it in mean field. Here you can do the calculations. You can solve the statistical physics of this. This is what these guys have done at the time. And what do you find? You find all the transitions predicting by random first order transition theory with the TD and the TK. Okay, so that model then is very nice. It's very confusing. I hope you're all confused. What is it doing? It seems to be defined like the kinetically constrained lattice gas model I've shown you before. These guys had the physical intuition that if you don't have enough space, you cannot do much. It's the same physical intuition that you put there, but you put it in a slightly different manner, either in the configurations or in the kinetics. And the way the system is going to behave is so orthogonal to each other. These guys have, kinetics controlled by the rare defects. And these guys, at least in some mean field limit, they have all the physics of the mean field spin glasses, starting from a completely different, again, macroscopic perspective. And so this model has a little bit of this, but it also has a little bit of that. And then you do your simulations in 3 dimensions. You see so dynamics, growing length scales. It's all looking good. So what is it then? Is it like a good model in finite dimensions displaying random first order transition, or is it a model controlled by defects and it's up in the air? It could be both. We don't know is the good answer, but it's an interesting model in the sense that it can be both controlled by defects or by thermodynamic phase transitions. And then you go to 3 dimensions and you don't know, just like we don't know what molecules are doing in the experiments. They could be doing one or the other, or the many that I haven't described in the lectures. And this is what we have. We have this gigantic zoo of different lattice models for glasses, and each one is giving a different perspective. And then again, your job as a statistical physicist is to, first of all, learn about all these tools and scenarios, and then try and use those to interpret the experiment in the best possible way. Thank you. So, you had a question?
This model, how do you evolve it as in simulations of what are the dynamics of this model?
Good question. Sorry, I should have said that. So I gave you the how the configurations exist or don't exist. So in a sense, all the configurations that are not forbidden have energy 0, if you wish. Okay, and the forbidden configuration, they have energy infinity, and the allowed configurations have energy 0. And these are the energetics of the model. You're asking, how do I move the particles in practice? I didn't tell you. The only thing that you should do is, of course, invent some dynamics where these rules are, satisfied. That is, if you decide to move one particle, you need to make sure that you don't go into a forbidden configuration, one thing. And then the choices are multiple, and actually in 3 dimensions, for instance, we have used many different types of dynamics. The simplest is, say, I can only move one particle into a vacancy because there is nothing there, and I need to remember that I have a constraint on which configurations are satisfied. That's the simplest rule. You could also introduce whatever local dynamics you like. You could say, if I have one particle, I could also exchange the position of those 2 particles. That's similarly not too unrealistic. This particle could switch, provided that you satisfy the rules. And you can do whatever. If you want to study just the thermodynamic properties, then it's your choice to decide what Monte Carlo dynamics you do. So you can even do some kind of ground canonical simulations, if you wish, where you come and you put particles from a reservoir, you fill holes, or you remove particles with a chemical potential. That's one way of studying the model. Your choice. Many choices are possible, provided this is satisfied.
Then isn't the previous lattice gas model sort of a subset of this? That dynamics also explicitly prevents configurations where...
No, that's the whole point of it. It cannot be recast into one of those models. In the other models, the constraints are on the kinetics, but no configuration is forbidden. No configuration is forbidden in the previous case. Only transitions are forbidden. Okay, so that's really, really the key of what I'm saying today. If you didn't get it, I need to repeat it. In the previous model, you put no constraints on the configurations. The only constraint is by this non-interacting Hamiltonian, on average, the number of vacancies that I have is controlled by the temperature. But I have otherwise no constraints on how many. Some regions can be totally full, and here it's not possible, right? In the other case, you could fill your lattice, and it would be allowed. And you can have large regions that are totally devoid of vacancies. It's allowed. It's just super slow by the kinetic transitions. So again, in the first family, the constraints in which transitions are allowed, and some things you cannot do. But you can go in principle anywhere, but some transitions are killed. In that case, the transitions, they can do whatever, provided that you don't go into a forbidden configuration. So the constraints in the configurations and not the transitions. This is why it was so obvious to me. I didn't even specify the kinetics because I said the constraints is on the statics, and you were confused. I didn't give you anything. So there are no constraints on the kinetics. Particles can do whatever they like. There is no finite number of things to do this. The constraint is I should not explore configurations that are forbidden. Thank you for the question. And then?
How would free energy look like in this case? I mean,
which case? Sorry.
in this case, when
This
it
one?
evolves.
So everything I said about chapter 2, random first order transition, applies to this one. And that's what I was saying here. If you do your thermodynamic construction for that guy, you find everything that you find in the P-spin model, everything.
Thanks.
Okay, I think he had the question for a long time, but so go ahead and then you go.
Yeah, so part of my question was his about the dynamics. So I have a comment. Isn't it like you have a rigid body, like let's say 2. So it's like a dimer, and you move dimer like this, so that no dimers cannot overlap. And in that case, is it possible to compute the entropy and which has the same behavior as sigma f that you were talking about?
First of all, I mean, if you're, I was trying to go fast, so I didn't give you like the details of the specific model that we see, for instance, in 3 dimensions. One problem, of course, that these people got immediately is they put those models on the lattice in 2 dimensions, and the first thing the system did, crystallize. Okay, So the usual business, even though it's a lattice model with some constraints, the same problem happens all the time, the crystal re-emerges. So if you want to study lattice models, I'm trying to answer your question, I'm just making. If you want to construct models of glasses like this in 2 or 3 dimensions, you have to make them more complicated than just one type of particle. You make them bi-dispersed, tri-dispersed, continuous. You have to introduce some more complexities, play with these constraints in a way that you keep the glassy dynamics, but you kill the crystal. Once you've done this, your idea of dimers or stuff, it's complete. Let me just finish.
Okay.
The idea of looking at dimers and stuff, it doesn't help at all. The system then has become a complicated mixture of things with holes that have a complicated geometry. So at the end of the day, you have a model for which no simple picture of defects diffusing around can be used. And so it's becoming a complicated glass model in 3 dimensions for which you need to apply the tools that people use for molecular dynamics, but no dimer, no nothing.
Okay, I see.
So when you look at the configuration, you look at all the particles, they do satisfy the constraint that you have a finite number of holes that are, positioned in such a way that you find, one configuration. And of course, if you want to increase the density of this system, it's more and more complicated to construct a configuration that's not forbidden. And then when you start moving, there are many configurations you can no longer access. So it's as if, that's why I started, I think. If you start to exclude, very many, part of your configuration space, and you're here, you would like to go there, but how do you go? You have to, So this is how the complexity and the glassiness emerges, that if you're sitting in one configuration, going to a new one, it's not easy because when you have so many particles all over the place, it's not easy to move things in such a way that you'll never go through. And so you can think of, to move from here to here, you have to squeeze in a narrow corridor, and finding that path takes a very long time. So that's a possible way of thinking about slowness, and the fact that the more and more constraints you have, you're very close to, in configuration space, closing those pockets, and this is how the pockets really emerge in the larger dimensional limit. So it's as if, you happily found by chance or because you waited long a good configuration. If you want to find another one, there are so few left available that it's complicated. And that's the story that I've been telling you about the entropy of the packings. Thank you.
Okay. Okay, so can you hear me from the back? Yeah? Okay. So let's get started maybe. All right, so good afternoon everyone. So we'll continue with this the statistical properties of a searcher who is undergoing different type of resetting mechanism. We'll sort of try to delve deeper into more fundamentals and some, and we also would like to do some applications to the realistic applications. Okay, just a short recap. So what we had so we studied the general formalism for first passage probability or survival probability of a searcher, of an agent, of a undergoing resetting. We derived a general formula which is given in terms of the underlying process, right? And then there was this critical question of when and why resetting is going to be useful, right? So we spent some time on that, and eventually we derived a condition which is called CV greater than 1, right? And we saw like how the CV condition actually works and what it physically means. All these things we did, right, in the last class. Okay, so again going back to this plot so that you again like refresh your memory. So you have this underlying process, the reset free process, right, which has a mean t, and then it has a fluctuation, right? And the CV is given by sigma t by t, right? Okay, so what you cannot see, is it? It's fine. Okay, so let me just draw this line in here. Okay, so what we showed, like what I showed yesterday, that if you have something like this, so then there is a very big broad spectrum of CV, right? And this, if you remember this picture, then of course that this is essentially the take-home message. So here you have something like CV equals to 1, right? So this is the part of the distribution which I would call narrowly dispersed. You can call it also sharply dispersed if you wish, which essentially means that the underlying process, the distribution of the underlying process is quite narrow, right, around the mean, so that the fluctuation is quite less, right? So this is when CV is less than 1. And then of course, like the CV keeps on increasing. So here you start seeing like, you can just call it like broadly dispersed. So we are still looking into this regime up to some time in the parameter space when CV is still finite, right? So, I mean, you have CV which is greater than 1, so their fluctuation is large, etc., but you still have these quantities finite, okay? So I'm looking into there. But then, of course, after some time, you will have all these quantities diverging. Like mean could diverge, the standard deviation could diverge, right? So this is essentially the widely dispersed regime, heavy tail power laws, etc., depending on what kind of powers, etc., you choose. And of course, we saw examples like diffusion, which is falling over here. And this is the case, like this entire spectrum where everything is finite. We exploited this drift diffusion process and went from here where you had a very high drift dominated regime to a place where you have more or less diffusion dominated regime, right? And so this is the place where resetting is useful, and here resetting is not useful. So this is the schematic we made yesterday, and if you remember this, sort of you will understand how resetting works. Okay. So what I'm going to do is in another 10 minutes, 10-15 minutes or so, I'm going to take a break from resetting. Okay, and we are going to learn something about something called inspection paradox. Okay, so inspection paradox is is a very nice result, a very counterintuitive result, which comes from probability theory. Okay, and this William Feller, like I think many of you guys will know, this, who has a book on probability theory. So in his second volume, he posed this problem, and then of course he gave the resolution. So let me just talk about this inspection paradox. So the best way to understand or illustrate the inspection paradox is just looking at some bus arrival processes, so, or some event being, like an event taking place. So imagine that you are in your favorite bus stop, okay, and these buses come and go, right, and then they come in different waiting times, right, different random times. So I'm just plotting a timeline, right. So this is my time axis, and this is your favorite bus stop, okay. And let's say you are waiting here, and then a bus comes, so this is like 0, the next bus comes at time t1, then another one comes at t2, right? Then these are all random intervals, okay? The next one maybe comes at t3, something like that, okay? And you wait till some fixed time, okay? Because you cannot just wait in a bus stop for a long time, right? For indefinite time. So let's say that you just wait till a fixed time t hours, and in between these are the bus arrivals, okay? This is clear? Okay. So these bus arrivals, as you can see that this in inter-arrival times, like they fluctuate, so they will have a distribution, right? They will have a distribution. So we can define the mean of the distribution by this. Okay. So this is our setup, let's say. Okay. So we have a bus stop, and then their buses come, come and go, come and go. There is a waiting time between these bus arrivals, and this is how I define the mean waiting time. Okay. Okay. Now let us play a game. Okay. So now this is a very well-defined process which is there in some bus stop, and you know the typical frequency at which bus arrives, right? Okay. Now as a passenger, right? As a passenger, you just arbitrarily start sometime from your home, right? And you arrive at the bus stop, right? And most of the time when you are arriving at the bus stop, the bus is not there, right? How likely it is that you arrive and then the bus is just there? It is possible, but most of the time you will see that the bus is not there. So what you are going to do, you are going to wait for some more time, right, till the next bus arrives, right? This is what you are going to do. Okay, so this interval is t3, okay? So okay, so this is what you do. So let's say that you wait some time, and let me just, for the sake of convenience, let us just define it by a different random variable, t res. Res is residual. It essentially means that you are arriving at the bus stop, you are waiting for the bus to arrive, right? So what is the residual time for you, right? Okay. And then of course, like you do this exercise again and again and again. So every day you arrive at the bus stop, the bus is not there, you wait for some random time. Then of course there is a statistics also for this random variable, right? Because every day you don't arrive at the bus stop and wait exactly 4 minutes, right? That time also fluctuates. So we also have a mean of that residual time. Correct? Okay. Now I want you guys to think about it, and what do you think about the relation between this guy and this, okay, in the following sense. So let us say that you arrive, at random between these bus intervals, right? And you wait for some time till the bus arrives, right? So what should be this mean average of this residual time, okay, with proportional to this one, okay? So let me just simplify the problem even more. Let's say the typical average time, okay, between two bus arrivals is 10 minutes, okay? What do you think your waiting time would be on an average? Will it be greater than 10 minutes, less than 10 minutes, or maybe equals to 10 minutes? Sorry? You are saying equal. I need more answers. Like less than, right? This is what you would anticipate, because I'm falling in between, right? Okay. So this is what. So the relation between this guy and this guy, actually it has all the possible effects. It can be smaller, as you are suggesting. Somebody said equal. That is also possible. But then the paradox comes that on an average, this also could be larger than this. Okay. So the waiting time for you at the bus stop is actually can be larger than the than the typical bus arrival times. Okay, so this is the paradox. Okay, so this is what the inspection paradox is. Okay, so you are not bothered by if it is lower, right? You are also not bothered by the fact that it is equal, but you are bothered by the fact that it is actually greater than t, right? Okay, so what I will do is I will try to give, we will try to derive a formula for this guy, okay? And then I will try to explain how you can actually resolve this paradox, okay? So let us first try to derive what is the mean average, okay? Mean residual time, okay? So to do that, so let's just imagine that you pick one of the intervals, okay? So this is, let's say, your ti, some ith interval, right, somewhere here, okay? And then you arrived at some random, right? You arrived here, correct? And then as soon as you arrived, you have a stopwatch, you start that stopwatch, right? So this stopwatch essentially starts from there, okay? And so, but you could arrive, let's say this, you could have arrived here, right? And also you could have arrived here, right? It's completely random, right? So if I have to think about the residual time, which is basically the remaining time, as a function of my stopwatch, right? So if t is equal to 0, so t is equal to 0 means that I am almost at the starting of the interval itself, right? I have just arrived when the bus left. So I have to essentially wait till the entire time, correct? So this should be, if I have to write this, so t is equal to 0, it should be the entire interval, right? But then if you can also have the possibility that you are also arriving almost at the end, right? You are very lucky, you arrive and the bus has almost arrived, right? This also is possible. So this is, let's say, ti minus, okay? In this case, it just becomes 0, okay? And of course, you have all the possibilities in between. So now if I want to draw a trajectory for t residual time, okay, as a function of this running time, okay, between all the intervals, one after one. So let's say it will start from here, it will go like this, okay? It's actually not a correct picture, so let us draw this picture more carefully. Okay, so t is equal to 0. It starts from ti, right? Then exactly at t is equal to ti, it becomes 0, right? So it should be equal, right? Okay, so this is my t1. This is my t1, and then again in the next interval, you know, like I don't know, I wait for some random time, right? These are all random times. So this is t1, this is t1, this is t2, this is t2, something like this. Okay, is it clear? In the back, is it clear, this one? Okay. Yeah, so t, what is t? T is basically you have a stopwatch, let's say, right? You arrive and you switch on the stopwatch, right? So it's basically running time, which is ongoing, right? So if you, let's say that if you have just arrived here, just after the bus has left, right? So you have to wait till the entire interval, right? So this t is equal to 0 is the entire interval, right? So this is what I'm plotting here. At t is equal to 0, this is basically you have to wait till the full interval. And what is the other extreme? When you are arriving just before, you know, like the bus arrives, right? So then you hardly have any time to wait. So this is where it goes down. And in between it can be anything. So this is a random trajectory, right? This is what I'm plotting, right? And then of course, I wait till some fixed observation time, right? So this, let's say this keeps on going, and let's say this was some sort of, say, and then this is my t ops, okay? And here, you know, like I have not completed the process. So it's not really a triangle, but it is some sort of a, it's some sort of a finite area, okay? This is the last one. You understand this one? Okay. So now what we want to calculate? We want to calculate this T residual average, right? So this T residual, right? So the empirical average would be, so I have to just sum over all of them. This is area under the curve, right? So if I formally write this, so it should be 0 to T obs by T obs, right? Yeah.
T2 can be greater than T1.
Which one? Yeah, that can happen. Yeah, of course. I mean, it's not gradually going down. Okay, it's nothing like that, right? So you could have this one. Let me make this one like this. Maybe this one is the largest. It should be equal. Okay. This is Tn. Let's see. This is Tn, and this is the last. Okay. So now what I can do is I can break these 0 to T obs into all the intervals, right? So in the sense, I can just write it, and these are all area under the curves, right? So I can just write it in the first interval. So this is et, so on and so forth, right? And then there is this final area, right? So the final area is essentially whatever it is. I need not calculate. It will be evident, like why I need not calculate this actually, okay? But I'm just defining that to be as a delta, okay? And then of course T obs, you can just write them in a simple way. So it's like T1 plus T2, all these things, and then the final interval is delta T, okay? This is my delta T, right? This last interval, okay? So if I do this, right, for the first interval, what is the area? Just 1 second. I will just finish this calculation. 1 by 2 T square, right? Okay, so this is half T1 square, then it will be half T2 square, right? And then delta. So similarly, you will have this one, it stays delta T. Okay. T obs is the fixed observation time. It's a very long time up to which I am observing the process. It's a fixed time, okay? So this is my empirical average, right? This is the way I do it, right? And now if I want to get to the ensemble average, what I will do is I will divide it by the number of intervals I have, right? Which is n going to infinity, right? So I will write it in the following sense. So I will have 1 by, so you have 1 by n. I'm dividing the numerator by n, also the denominator by n, right? And here I have half summation over Ti square, and then the last one. Similarly, I have 1 by n summation over Ti, then I have delta T, right? So now n going to infinity limit when I am basically, when I have a very long observation time, right? So I can safely ignore these terms, right? Because I know that this is a finite quantity, this is also a finite quantity, okay? If this is so, then what do we get? So this is what? So this is T square by 2, right? T square, right? It's an empirical average. I have divided it by n, so it becomes an ensemble average, right? T square by 2, and this is T. Okay? So now if I just do this, just one line, what I will get is the following. Okay? 1 plus sigma square T by t square. Okay, I'm just rewriting this. Okay, I have t square by 2, right? So I write t square minus by 2. I take the half over here, and then you subtract the t minus square plus add it, and then just do some, do some small algebra, and this is what you get. Do you identify this guy? CV square. So I get t by 2 1 plus CV square. Okay. So now go back to the schematic, right? You had for the bus arrival, right? So typically the buses were arriving on an average with t, right? Here using this was the typical bus arrival, right? And now what we derived is your average waiting time. Once after you randomly arrive at some interval and the residual time you wait, if you calculate the average of this guy, it actually doesn't only depend on the mean, but also it is sensitive to the fluctuation. Okay, this is the most important, the most crucial fact here. Okay, so I have t by 2 1 plus CV square. Okay. So it is now sensitive to fluctuations. Okay. Now let us take a couple of examples. Okay. Let us take a couple of examples and let us try to establish whatever possibilities we got. We got 3 possibilities, right? Okay. So first was, let us take a process where the buses come exactly after 5 minutes, right? What is this? What is the value of CV in that case? 0, right? If CV is 0, so then what you get? You see that it's t by 2. This is what you would have anticipated, right? Typically, if I arrive at some point of time, if the buses are very punctual, I have to wait exactly half the amount of time, right? Now let us take one example. CV is equal to 1. Okay. So now CV is equal to 1. What happens is that this t residual becomes exactly t. Okay. But then there is this case of CV greater than 1 for high variability. Okay. Like whenever you have large fluctuations, then what happens? Then t residual becomes greater than t, right? Okay, so mathematically we can now see how the residual time can be greater than the original arrival time, okay, when you have very large fluctuations on the bus arrivals, right? So now what we see here also that again you see that something is happening again with the CV, right? You see that we did this CV calculation with stochastic resetting. We got this CV greater than 1 condition. And now this is something else, right? And again, we are back to some condition where CV is equals to 1. And it seems that CV is equal to 1 is a boundary beyond which you get something which basically gives an non-intuitive result. Correct? Okay. So, of course, then if this is the case, so we have to actually relate between the stochastic resetting process and also this inspection paradox, right? There must be some connection. Okay, it cannot be, like so accidental that there also is a CV criteria and also there is a CV criteria, right? We must be able to make a connection between these two. Okay, so before we do that, what we do is what I would like to do is I will like to give you the resolution of this paradox, right? So why this is happening, right? Mathematically, you understand what is happening, right? But in principle, what is happening, right? So you see that the buses. So let me just erase this part. You see that typically, because it fluctuates the time, so there are some intervals which are small and some intervals which are large, right? That is what gives rise to t. You have t1, t2, t3, right? You average over them and you get this, right? So it essentially means that some t's are small, some t's are large, right? Now the point is, greater weights are given to the larger intervals. Okay? So that is that is basically giving rise to something called a sample bias. Okay, so you have, when you arrive at random, it is more likely that you will arrive at the longer intervals, okay, which is greater than the mean time itself. Clear? And that is the reason which is behind this inspection paradox. So on an average, the time you have to wait after arriving at some random interval, okay, the reason why it is becoming greater than the mean arrival, because you are always coming at these bigger intervals, okay, and this usually will happen when you have very large fluctuations, okay. Yeah. So this point, right? Yeah. Okay. Okay. So you see that this is, again, I am drawing that timeline where these are the bus arrivals, right? So these are like T1, T2, T3, something like that, right? So some intervals are small, some intervals are large, right? That is what gives rise to this one, right? So the reason why this thing is happening, okay, because you are arriving at the longer intervals, okay, and these intervals are actually, the size of these intervals are even larger than the mean time itself, okay, and greater, you have more weights to these larger intervals, okay. So this is the reason why the mean residual time is becoming greater than the underlying arrival time. That is what, so that is what I said, greater weights are given to the longer intervals. So this is what we call sampling bias, okay. Yes.
Number of smaller intervals can be more than the large intervals.
Come again?
The smaller intervals.
Yeah.
Number can be much higher than the larger intervals.
Number of smaller intervals. Okay, see, on an average, right, for example, you will have both of them, right? So that is what giving rise to this one. So I am not really sure whether I understood your question that, like whether the number of shorter intervals will be greater than larger number of larger intervals. What I'm trying to say is that whenever you have these longer intervals, your arrival is more likely to happen there. It's more likely that you will fall into these bigger intervals, and then the average waiting time will be higher than the typical arrival times. Okay, the number is, like I think it's not really that is not the point here. Yeah.
I think what he put is like if the number of short intervals like that means the fluctuation is less.
So the fluctuation essentially is coming because the waiting time, it's coming from the waiting time, right? It's coming because you have longer waiting times.
Variability is less means the time of arrival is also smaller. So interval of kind of, but then it's scale.
No, the variability smaller essentially means that the intervals are of the same size. Okay, you see the number of intervals we are already assuming it to be large, right? This is how we derive it, right? Okay, so I think we are on the same page, to understand how this inspection paradox works and what is the resolution of this, right? Now we are a bit of puzzled because we see again the CV criteria coming here also, right? So what is its connection with this stochastic resetting? Okay, so we'll try to accelerate this discussion now, because I'm running a bit late. Okay, so you see that the way we derived this CV criteria for stochastic resetting, okay, that was in the linear order, right? So we assume that, okay, if you just perturb your underlying process with a very small delta R, right, then that is the condition we probed, and then we got this condition, right? Okay, so this is something just keep in mind, okay, that this is the assumption we made. So you, in a longer interval, there is only possibility of having hardly one or two resetting events, okay. This is something just keep in mind. This is what it would mean, delta going to 0, okay. Okay, now let us look into this, a stochastic process, okay, with some process completion, okay, in the sense that assume that I have a process, okay? Okay. Just give me a second. Yeah. Right. Okay. Okay, and let's say that the process will stop when it will reach there, right? This standard thing. Okay. Now let us try to do the following exercise. Okay. First, we inspect the process. What is this inspection? Inspection essentially means that you have this process going on, right? You just randomly arrive at any point of time in this trajectory. That is the same as, imagine the bus problem, right? So the buses are coming and going, right? So there is a stochastic trajectory, and as a passenger, you just arrive at some random point of time, correct? So you have this ongoing process, right? Which let's say starts somewhere and ends somewhere, correct? And then you arrived here and you inspected the process. Okay, but you didn't do anything. You just came, inspected the process till it got completed. Okay, same as the bus arrival, right? You came and waited for the bus till the next bus came, right? This is what I am doing. So there is this trajectory which will complete at some point of time, but I am just arriving at some random point of time and just waiting when it will end, right? So this would be my T residual, right? Correct? Okay. Now let us do the other exercise. What is that exercise? I arrive at the same point, but now I reset the process. Okay? So I arrive at the same point of time, okay? But instead of just, just waiting for the process to complete, I now part of the system, okay? I part of the system by resetting it. So when I reset, let's say that it resets to some initial condition, right? And from there it will start again, right? And now you just try to recall what I said here. So I said that delta R going to zero limit, right? So delta R going to zero limit is that you can have hardly one or two resetting events, right? So I'm assuming that after this one resetting event, the process will complete by itself and there will not be any other resetting events, right? So after resetting, if the process completes on its own without having any resetting, what is the typical waiting time for that? That is the same as the underlying process itself, right? Because I came, right? Imagine the following condition, right? Following situation. So you have started somewhere and then you are completing the process, right? We are without undergoing any resetting event, right? So that is what is happening. So by taking the delta R going to zero limit, you are just ensuring that there is no repetition of another resetting event, correct? So you resetted the process and the process will end at some point of time, right? And this time, let us call this T, right? This is the way we are defining this guy, right? So now let us invoke the condition, when is resetting going to be useful, right? So if I arrive at some random point of time, do not part up the system, let the process continue and finish, right? So then the waiting time is on an average T days. T residual, right? And then you have the other case when I arrived and then I just reset the process, right? And then of course, also I assume that it is in a smaller limit, so I cannot have another resetting event. So then what is the typical waiting time? T, right? And now if resetting has to help, right? So what is the condition I need to invoke? So the condition I need to invoke is that this T residual time has to be greater than this, right? For restart to help. On an average, right? Clear? This part is clear. I hope this part is clear, right? Now use this condition. You know the formula for this, right? What was the formula for this? T square by 2T average, right? And you have this guy. Just rewrite this condition and what you will get is CV greater than 1. Okay? So this is how the inspection paradox, okay, we can make use of the inspection paradox also in the context of stochastic resetting to understand how resetting works. Okay? And what is the usefulness of perturbing the system with some small resetting rate. Okay? So I think, I hope you guys have understood what I wanted to say here and this connection with the inspection paradox. And if you have not, then you can ask me further questions maybe during the tutorial. Okay? So with that, I will just move on a bit because I have to finish a few more things today. Okay. So I'm erasing the entire board from this side. Okay? Cool. So far, you see that what we did yesterday, right? We were trying to write these renewal equations, and we were trying to write the mean first passage time under Poissonian resetting, right? And then there were many questions about what happens when these resetting times are not coming from Poissonian distribution, or like exponential waiting time, but they're coming from some other distributions, right? What happens? How can I write the mean first passage time under that kind of resetting process? And of course, generically you can ask a very broad question like, there are endless ways resetting mechanism and first passage processes can mix, right? So can I think about a general formalism, okay? Because the formalism we developed there, we needed to probe the fact that the resetting is happening with a Poissonian rate, right? That's why we had these exponential times. Right? So now we would like to come up with an approach which doesn't really, care about all these details. So some sort of a black box approach, okay? So this is what I'm going to do. I'm going to teach you guys a black box approach, essentially. For first passage under resetting, okay? So lose all the details, at least on the derivation level. Okay. Okay. So we will start with this following schematic. Okay. Again, this is a schematic we have used also before, but this will be used in a different context now. So let's say that this is a process which starts here and finishes here. Okay. Okay. So this is what I would call, this is just a schematic. Okay. There is no axis, etc., etc. here. I start from somewhere and my process ends at some random point of time somewhere else. Okay? Start, finish. And what is the typical time it takes? Let's call that random variable t. Okay? So this is my first passage, underlying first passage time. Okay? This is a random variable. Okay? Now imagine this situation, imagine the following situation where the process, let's say that whatever the process is, it's going on, it's an ongoing process, and at some point of time you reset the process. Right? So let's say, again, it's not really an axis, time axis, but you say that at some point of time, maybe you just reset and put it back to the initial condition, right? This initial condition can be anything. Okay, I'm not really saying that this is a fixed initial condition or something like that. It could be an identical condition. What is important that it has to be identical condition, because again you are starting the process from the same initial condition. Correct? Okay. So now let's try to understand it slightly better. And then the whole thing, let's say first passage process which is undergoing one or multiple resetting events, let us denote this entire completion time by this new random variable t subscript capital R. Okay, this is my new random variable and this is my global completion time. Okay. So I want to write an equation, okay, a governing equation, a stochastic equation for this. So you see that the crucial difference here is that all the time, all the way here till today, we have written mostly a renewal equation or some equation for the probability distribution, right? So here what we are going to write, we are going to try to write a renewal equation for the random variable itself, okay? Let us see how it can be done, okay? So let's first imagine that you have a process which started here, ended here, okay? No resetting event, correct? Let's say no resetting event. So this is n is equal to 0, okay? So what will be your TR in this case? No resetting event, right? So TR is just T, right? Okay. Let's take the next case where let's say one resetting has happened at some point of time. And let's just call that resetting time as R1. This is a random variable which is coming from the distribution of R, right? So let me also write here. So the distribution for the underlying process is Ft, and the resetting time distribution is R, okay? And I am not making any assumption on T and R, okay? Okay. So now some random variable is coming from this distribution. When it comes, the process is restarted, right? So it goes back here, okay? So I can try to write this guy in the following sense. So let's say TR is equal to, I add this random variable R1, correct? So I am here, right? From here, moving forward, I cannot see what is going to happen, okay? So then what I can do, I can denote as if like the process has started, right, afresh. So I can just write TR is equal to R1 plus TR prime, okay? So what is this TR prime? Because you see that when I reset the process, right, it went up here and then it came here, right? And from here it started again. And a priori I have no idea how long will it take, right? Whether how many resetting events that can happen in the next, right? So the way I should write it is again in terms of the main random variable, which is TR itself, but because the process has started from scratch, right? So statistically is the same random variable, okay? But of course the value is different, okay? So I can basically play this game, okay, for one resetting event, two resetting event, three resetting events. But the scratch here, the take-home message here is that if you have a process TR, so it has basically two possibilities, okay? So TR can be T, okay, which is basically this case, right? But this, out of all the events, this event, each one of this event actually happens with certain probabilities, right? So the first one, let's say, this happens when T is less than R. So you can imagine that you have two clock, right? You have two clock. So let's say this is my clock for T and this is my clock for R. Okay? So if this clock gives a shorter time, right, then of course this event will happen, right? This event essentially is the first passage event. So you add this quantity to the global time. Clear? If this doesn't happen, right, so then you just unnecessarily waste a certain amount of time, which happens to be the resetting time, correct? Because you resetted the process, and when you resetted the process, you went up to some time and only then you reset, right? So the waiting time was R1, R2, R3, whatever. So generically I write it as R, right? And this basically takes me to the initial condition, from where I have to start again. Okay? So I should write TR prime. And this is happening with the condition that R is less than or equals to T. Why? Again, look into this picture. So you have a resetting watch, right? You have a resetting watch and you have this. So basically there are these two clocks which are taking place, right? Giving you random times. Now resetting event has happened before. So and this is the reason you have to go back to the scratch and then start again. And this is a recurrent process. This is a renewal process. Okay? Because TR prime, again you can write another equation for TR prime, right? But whatever that equation is, that will also include again TR double prime. But then all this TR double prime, they are all equivalent. Statistically, they are all equivalent. Correct? So this is basically our stochastic renewal equation for the completion time under resetting. Okay. The main point here is that I am not making any assumption on R and T. Okay. So let me just rewrite this equation. Okay. So you can just rewrite this equation in the following sense. So first let me write it and then I will explain. Let me just see. Okay. So I will explain what is it. So this is a new random variable which is, I denoted this by minimum of 2 random variables. Okay. I will explain what is it in a minute. And this is a new random variable, okay, also. But this is as a rather simple definition. Okay, this is like a theta function, okay, if you wish. So this guy takes a value 1 when r is less than equals to t, otherwise 0. Okay. So now you can do this maths, right? So for example, let's say that if r less than equals to t, so this becomes 1, correct? And if r less than equal to t, then which is the minimum? R, right? So then it becomes tr is equal to r plus 1 times tr prime. That is what is this one, correct? And the other one, of course, you can see that if it doesn't, this is 0, so then the minimum is just t. Okay? So we see that this is basically just a, like a rewriting of that renewal equation. Okay. Yeah. Right. Sorry, come again? Yeah. So, if you remember the schematic, so the initial condition, now you don't need to even think about initial position itself. Just think about an initial condition, which is not really a fixed position or a like something like that. You could have an identical ensemble, right? So you think about it as an initial condition, but it has to be an identical initial condition. That is correct. Yeah. That is what I say. So tr prime would also will have t again the same structure, right? It is not, right? So tr prime also you can write in terms of again this another next resetting event. So it's just a renewal equation. So you need not even need to write it, right? Because this tr prime will have all the information of moving forward. You had. Of course. They are taken from the same distribution. It's just a different copy of that. Because this is a new copy after it has started from the initial condition again, right? Yeah. You had a question, yes? Okay. Okay, so now what we can do, and okay, so I didn't tell what is this minimum of R and T, right? So what is this minimum of R and T, right? So this is, as I said, this is a random variable, which is basically calculates the minimum of 2 random variables. Very simple to understand. Imagine that you have 2 random variables, Z1 and Z2, right? Choose any of your, like favorite distributions for Z1 and Z2. They are different random variables itself, okay? This one may be from Weibull, this is from exponential, I don't know, like whatever you want, okay? And of course, you do many realizations of this, you get different numbers, right? 2.14, 3.14, 6, 0.3, 8.9, right? They're independent, right? You do this one, right? Then you make another column. Minimum of Z1, Z2, right? So in this case, which is the minimum? This one, right? So this is 2.14. In this case, 0.4. Let's take another one. So let's say this one is 0.3, 0.1. So this one, right? So if you take an ensemble of this, if you take 1 million numbers like this, right? So this is a new random variable. which just takes care of the minimum of 2 different random variables. Correct? You understand? And of course, you can also do another thing. You can also keep a counting variable. What does it mean? A counting variable which just counts the number when Z1 was less than Z2. Okay? It will be clear in a minute why I am doing this. So this is very simple. So let's say that if Z1 is less than Z2, only then it picks a value 1. Okay? In this case also, right? And in this case it is 0, right? So it keeps on going. So if you do an average of this, you will get a number for this, right? Okay? Okay. So I think it is clear how to calculate, how to compute this minimum of 2 random variables and also this guy, Z1 less than Z2. Now let's see that how it is relevant to our calculation. So what we can do is we can take an average on the both sides of this equation. Okay? So when I say this average over all the possible random quantities you have in your system. Okay? So if I take an average, so you get minimum of T and R, right? Then you have this guy. But you see that this TR prime is coming in the next event itself, right? So these two are uncoupled, correct? Okay, so these two guys are uncoupled, so I can just write them as this. Do you guys follow? Okay, very good. So what is this TR prime average? Sorry? Same as TR average, right? So it's the same guy. So I just write minimum of TR, right? This I will write, then this is TR. Okay? And what is the average of this random variable? Okay? This is a random variable which takes the value 1 when this condition is satisfied, otherwise it takes 0. Right? How do I write an average for this guy? Okay? So if I have to write an average of any quantity which has multiple possibilities, right? How do I write it? I write with the probabilities. I write the probability that this possibility is happening, right, and the value it takes, plus probability of the next event happening and the value it takes, correct? So if I do that, so the average is, this I average is 1 times the probability that this is happening, right, plus 0 times probability the other event is happening, right? But in this case, it is 0. Okay? So then I am left with probability r less than equals to t. So this is what I would write here. So this is probability r less than equals to t. Okay? Now I have TR here, I have TR here, so I can take it on the other side, right? So I can take it on the other side. So then I have minimum of T and R, and then we have 1 minus probability r less than equals to t. Okay? But this is the probability, right? This is also less than equals to 1, right? So then this is how I can write it. It is exactly the complementary way I can write it, right? So I can just write it in the following sense. So minimum of TR T less than R. Okay? Is this clear, this expression? Okay? So let me just rewrite it here. So I can just write the expression here maybe. Okay? Okay. So I have this expression, right? TR is minimum of TR probability T less than R. This is the expression. Now again, go back to the original schematic, right? So I have what I had assumed that I have an underlying process, any kind of first passage process. I'm not even giving the form of it. It could be a random walker, or it could be a random variable which is, like designating an income dynamics. Okay. completely different, right? Or a motion of a chemical molecule or something like that. Okay, I have a first passage process, and then I want to add a resetting on top of that, right? If I do that, what I get is something like this. And now I had written Z1, Z2, Z3, right? So now I can just replace them by T and R. So this should be minimum of T and R, right? So I just basically pick 2 clocks. I manually do all these things, okay? Without even knowing what is the process I'm looking at. This is the reason I call it a black box approach. So for example, there can be many processes for which maybe you don't know exact form of the first passage time statistics, right? So you remember all the examples we did yesterday, we needed to know the explicit form of the survival probability, right? Or the first passage probability for the underlying process, right? This is something which we needed. Now assume that you are doing some sort of a complex process for which you do not really have an exact formula, but rather what you have is a first passage statistics, is a data, right? It's a numerical data. You can have a numerical data, right? Need not be an exact form of some function. You get a numerical data, you plot it. So this is the data I'm talking about. Somebody gives you this data, I'm happy with it. If I want to add resetting, this is the way I can just add resetting, okay? So what I will have, somebody will also give me that, like I want to reset this process with certain rate or something else, okay? I'm also not specifying the resetting mechanism as such. But that also has a waiting time, so I am also getting a lot of time series, like a time series with full of resetting in times. I just write them together. For each one of the case, I calculate minimum of T and R. And in individual case, I also calculate when this guy is smaller than the other. Right? When I do this statistics, hey, this one gives me probability that T less than R, right? So this basically counts how many number of ones you had, right, divided by the total number of samples, correct? So this is basically how you can calculate the mean first passage time under generic restart mechanism, okay? So you don't need to even think about whether it came from a Poisson resetting or something else. Okay. Now, I think what I will do is, okay, I still have quite some time. So there are 2 things which I will do. I will first of all try to what I sort of try to give you, tell you here that how you can actually numerically exploit this formula. Okay. But of course, like as a theorist, you sometimes would like to see some explicit formula, right? So to do that, I will just tell you guys in like 5 minutes or so how you can evaluate individual quantities in principle. So let's say you have this T, right? So it's coming from this distribution, right? And then you have R, which is coming from this particular distribution, okay? And let's say that you want to calculate statistics of this, okay? Okay. This is I want to derive a mathematical formula for this. Of course, I know I have already told you how to calculate this numerically, right? This you know, this have understood, and I think that is also much more intuitive to calculate it numerically, right? But let's try to derive a formula for this, let's say, okay? So how to derive a formula for this guy, okay? So for any kind of new random variable, whenever you get a random variable and somebody tells you how you calculate the distribution function for this, usually an approach is to calculate the CDF, which is the cumulative distribution function, okay? So let's just define this guy as Z, okay? I'm just defining this as a Z because it's a random variable and I'm interested in the statistical properties of this Z, right? So what is my CDF? I hope you guys know what is a CDF, right? Cumulative distribution function is the probability that this Z is less than equal to some fixed number, okay? This is the fixed number, okay? So this is what I want to calculate, okay? So this, I can write it in this following way. So 1 minus probability that Z is greater than T. Right, nothing, it's just, I just wrote the complementary probability, okay? Now let us put back this guy, this minimum thing. So the probability that minimum of T and R is greater than T. This is what I would like to calculate, right? Now, what do you think what is this expression for this guy? So I'm thinking about two random variables and the minimum of that random variable, and that is greater than something, right? So if minimum of two random variables is greater than something, so individually each one of them should be greater than that, right? Correct? And also T and R, they are independent. So I can break this, right? So I can just write 1 minus probability T greater than T times probability R greater than T. I hope it is clear. Okay. Now, so this guy and this guy is very easy to calculate. Okay. How can I calculate this quantity? This I think I have shown you guys before. So let's say that I have again some random variable. Okay. So let me call that random variable as U. Okay. And then let me say that I want to calculate this, right? How do I calculate this? So this is my random variable, and what is the distribution of this guy is something like this, right? And this has a lower limit, which is T, right? And of course these are all times, so they can go up to 0 to infinity. So this is infinity, the lower bound is T, so then this is, right? You remember we have derived something like this in the second class when we calculated the survival probability for exponential random variables and things like that. If you look into a note, you will find this. Okay. So what does it tell? On the more on a technical level, I started with the distribution of Ft and Fr, right? If I know these two guys, then I can calculate this and this by this formula in principle. Okay. For arbitrary distribution, whether I will be able to close this integral, that's a different question. Anyway, I am talking about technical details. Okay. And so this is the minimum of R and T. This is the cumulative distribution, right? So how do you write also the cumulative distribution in terms of the original random variable? This is also something you have done. So this is, right? So this is less than or equals to T, so it can go only from 0 to T, this guy. Okay. If you don't understand something, just let me know. Yeah. This one? This one? This one? Yeah. Yeah. No, these are two different random variables, right? T is a random variable, R is a different random variable. They are not related to each other. They are not coupled to each other. Correct? Okay? I mean, otherwise, of course, then it becomes what you are saying. Yeah. If the minimum is greater than something, so individually they will be, right? So this is what I have written there. Okay? So from usually these are all like very well known. So if you take the derivative, so this is Z is less than or equals to T. Yeah. So if you take the derivative of this, what you will get is you can write this Fz, the distribution of this guy, in terms of the CDF. Okay. So this is basically, these are technicalities, and what I'm trying to show is that you can calculate the average of minimum of R and T, and also the distribution of these things. Everything can be calculated exactly. Okay. So we started with this. Let's say we started with this TR minimum R T, right? Probability R less than or equals to T, right? So now we are in the position where we already know the distribution of minimum of R and T, right? So this is something we know because we know the cumulative distribution via this, right? And then in principle I can just take the derivative and get the distribution, and I will just write this distribution. I will not derive it here. It's not very difficult, so it's just given by the following. I'm just writing this because this will be useful for the next example. This Okay. So this is, you can derive this via this. So you can just replace first this one and then take a derivative of this. If you take a derivative of this, you will find this guy. Okay. And what is the probability that t, was it probability r less than t, or I think I made a mistake there, t less than r, no? Okay, so this is something you can again compute it quite easily, right? First what you do, you fix t, okay, because both of them are random variables, right? So you have to average over both of them, right? But how to do it, in your mind, how do you do it? First, fix one of them, okay? So let's say that you want to fix t first, okay? So I fix t, so then I get this, right? You see that I have written this guy over here, but I have just fixed t as a small t, correct? First I fix that, and now I vary this, right? So how I can vary this? With its own distribution, because this is something which I know. You can also do the other way around, okay? You can first fix r, okay, then vary it, okay, vary the other one. So you can do the following. So let's say I do this, probability t less than t, okay, and then you vary, and then this is the t corresponding to r, right? So I can write it in this. This is I think this is getting a bit more technical. So if you have queries, just clarify this thing during the tutorial, okay? But I just wanted to show you here that in principle, if you have this formula, this minimum of the mean first passage time under resetting, how you can actually exploit both the numerator and the denominator in terms of general distributions without even, like knowing why, because you see that there is no particle, no position, nothing, right? It's like fully working like a black box. You are just like, without even knowing what is happening. And then of course, now when you have to plug in the distribution for t or something like that, then of course you will need the details. But on the formalism level, everything goes through. Okay, so I think what I'm going to do is, like, we will do some examples, but maybe it is better if we do these examples during the tutorial. And I just want to, in this last half an hour or so, I also want to introduce something new to you, okay? So what I would like to do is that, so far what we have done is, when you have a stochastic process and you have something called instant teleportation, right? You have some sort of a trajectory, right? If you think about it, the way we have done so far. So we have done something like this, right? So you have, let's say you started from origin, and then you did this instantaneous resetting, right? And of course, this is, this is quite a practical hindrance, right? Because in real life, right? If you want to go from one place to another place, right? It will take certain finite time. So even if you want to do resetting, it should happen in a finite time, right? In principle, okay? So just imagine that I am doing an experiment, okay? So if I have to do an experiment, let's say that, like I have a colloidal particle, right, which is doing some diffusion, okay? Okay, and I want to do the resetting, okay? How will I do the resetting, right? So what I can do, what an experimentalist can do, okay, I think there can be many different approaches. One of the easiest ways perhaps to do is that whenever this resetting time occurs, in the sense like whenever you decide to reset, right? Because you have a given distribution for resetting, right? Which is giving rise to a set of random variables, R1, R2, R3, etc., right? So starting from 0, let's say first time the particle diffuse, and exactly at R1 time, you now want to reset. How do you reset, right? So far what we have done is we have not cared, right? We have like, even if I have at infinity, I will come back in 0 time. But now, like for example, somebody who is doing experiment, how does this person reset this particle? Okay. So one of the approaches would be that you can bring this particle in a finite time by using a laser trap or something. Okay. This is one of the approaches. So what you can do is that, let's say the particle exactly at the position, exactly at time r1, it's somewhere here at x. Okay. So what you can do is you can project a trap. Okay, you can project a trap. So when I say project a trap, what I essentially mean is the following. So you have this harmonic trap, okay, and you project the trap on this particle. Okay, so the particle is trapped. Okay, inside this particle is trapped inside this harmonic potential you have created using laser beam. Okay, and now you can modulate it to bring this particle from here to here, being trapped inside this well, okay, this potential well. So this, you manipulate this guy in such a way that it comes from here to here with keeping the particle inside. Okay, and as soon as it comes back here, you say the process has been reset. Is the mechanism clear? And of course now, like if you ask an experimentalist, there are many arbitrary ways you can actually reset the particle from this position to some preferred location. Okay? So what are the two important things here, right, when you do this finite time resetting? Okay? So first of all, of course, like it takes finite time. That is, of course, it goes without saying. The second point is actually a bit more crucial. Okay. Second point is, you see, in this case, as I just mentioned some time back, that it doesn't matter how far the particle was. You just reset it in 0 time, right? But you see that if you are doing the experiment, and if the particle has diffused quite far, right? And let's say now you are again projecting the trap. So this is your trap, right? This is your trap. You are holding the particle and bringing it back, right? Okay. So let's just define this time as, first time as tau1 and this time as tau2. Okay. So the second important ingredient is this tau should depend on the position from where it is coming. Correct? So if you want to be realistic, this is how you should model the system. Because if I now tell that, okay, I am just waiting for a very long time, let the particle has diffused very far. Okay. Now if I have to bring that particle from there, right, I have to invest some energy, because when I'm switching on the trap, there is a power being wasted, right? So, and then you have to bring the particle from there. So if it is nearby, it will take less time. If it is very far, it will take longer time. So this piece of information also should be there. So this return time, so from now onwards we will use this word. So this return time is spatiotemporally coupled. Okay, and of course there can be many different modes, like by which you can reset back, right? Various modes of return. This is more or less, is falling to the experimentalist's domain, where depending on who is doing experiment of what kind and whatever mechanisms they use. Some people would like to prefer to bring the particle with a constant velocity. Some would prefer to bring it with a constant time, maybe some accelerated motion, whatever is available. Okay? So, but what you can understand that there can be various modes of return, but it should have the following, this condition, that the far it is, it will take longer time to come, right? And then only it is making more sense, right? Okay, yeah.
Thinking that in this case, when we are resetting, we are assuming that the environment
Yeah.
So it will take a finite time for that particle to equilibrate with the environment.
So that is not something we are considering here. We are just considering the fact that it takes a finite return time for the particle, because you have to hold the particle and bring it back, right, by using some optical mechanism. This is what I am saying. It's not important that whether the particle has equilibrated or not. That's a different question. Okay? As long as we are concerned with the time it takes for this entire process to complete, this is the only ingredient we need, the return time and the mode of return. Okay? Okay. Okay, so I think what I'm going to do is I'm now going to use the same framework that we have done for this instantaneous resetting case, okay, and for arbitrary resetting time, okay, and I will try to introduce the same mechanism, same formalism essentially for this kind of process, okay. And you see that this was one of the realistic processes I wanted to introduce to you, but also there are many other processes. For example, you can think about many search processes. So, for example, out there, right? For example, all the foraging animals, they have their own respective dens. So they go out for resources, etc. But at the end of the day, they always come back at home, right? If you think about mechanical machines, for example, drones, right? So they go out, but then again, they have to refuel or recharge, right? So they have to come back to the docking station, right? So you see that these search processes, which has perpetual motions, but once in a while, they need to come back home. So there is there is a reason for them to come back home, wait for some time, like recharge, refuel, rest, whatever, and then again resume your search process. Okay. So this is the reason we need a home. First of all, this is our home. Okay. And then of course, whenever these natural search processes take place, it always takes time for these search agents to finite time to return to the home, right? And this is what we have introduced in the name of finite time resetting. Okay? And let's see how we can generalize the formalism that we have done for the instantaneous resetting for the case of home range search process. Okay? So this home range search process, I'm using this this phrase home range search because the search process is taking place based on this home. Okay? And this is also, you see, this is also falling into the category of the experiment, because you can also imagine this origin to be your home, and you just go out, okay, and then when reset happens, you just bring the particle with a certain finite time mechanism. Okay. So if we can somehow generalize the formalism, we will be able to capture this very broad class of search processes and as well as these experiments, all of them together under the same umbrella. That is the goal. Yeah.
Is this slightly different from a random quench process? Right? Suppose I suddenly turn on a harmonic track, but
right.
I do it randomly.
Right.
So in some sense, I'm bringing the particle, back to some location.
But this quenching is instantaneous quenching?
Yeah, let's say the quenching is instantaneous.
Okay. Okay.
So is this equivalent to an instantaneous random quench?
I think this is not, right? Because here it is taking time for the particle to come back. Right? But when you do the quenching you are saying, right, does that bring the particle or whatever the configuration instantaneously back to the initial condition?
Okay, so I was thinking of quenching from one frequency to another, but not to, if I quench it completely to a very high track, then it will be instantaneous.
It depends actually like how you quench the system, right? If you quench it, if it comes instantaneously, right, at what frequency probably doesn't matter, right? The different frequencies would mean that you are resetting to different frequencies. That is the way I would put it. But if the non-instantaneous resetting would mean that I need a certain amount of time for me to reset. That is what it means. So all kind of quenching thing, I think they are still instantaneous. It doesn't matter what frequency where you are quenching it. So it just basically your threshold changes.
Exactly. Sorry,
No, if it still takes time to return, of course, then it's.
You are changing, of course, instantaneously, but the particle takes time to.
Relaxation time.
So
Okay.
that will come under this category.
Right. So let me try to understand what you are saying, maybe. So let me just draw a trajectory x of t versus t, right? And let's say the particle diffuses in a potential, right? This is what you're saying. So let's say that I have some diffusion is taking place, right? And at some random time, right? Whatever your potential was, right? So let's say that your potential was well defined with a given constant.
So initially, let's say I don't even have a potential.
So let's say that you don't have a potential. Right. Oh, but the point is, once you make the switch, you also let the particle relax, right? Of course, then it falls into this category. Yeah. We'll derive one such example. Yeah. In particular, we'll derive exactly the example where, like in the case of experiment, what you can do is, let's say that you are diffusing, right? And at this point of time, I switch on the trap, right? I switch on the trap, hold the particle, and bring it back, okay, with a constant velocity. So this will be my trajectory. So let's say this is is a constant velocity, and then the particle is brought back here from where it starts the next trial. And this keeps on repeating. And of course, you can calculate different quantities, for example, position distribution. You can calculate the time it takes for you to reach the global target. These are the questions you can ask. And the whole point is, this time here itself, I'm saying that this is an arbitrary time, okay? And how can I generalize the formalism that we did for the instantaneous resetting for such process, where the system is actually coupled to where it is resetting from, right? Okay. So just keep this picture in mind. So let's say that, again, I have certain domain, okay? And let's say this is my home. Like you don't have to assume anything particular about this domain. The formalism doesn't really depend on this. And then let's just assume that you have many targets, okay? These are all targets, okay? And then I am here, and now I want to go back, okay? So I can go back in finite time, okay? Or some time, so let me just call it tau x1, okay? And x1 being this position. Now, so far when you did the instantaneous resetting, you didn't even bother about x1, right? It didn't even matter. But in this case, I have to keep track of this x1, okay? So let's say that the next, like you have gone there, and now let's say that it so happens that maybe you have some geographical constraints, okay? Some topographical issues. You cannot really cross, okay? So then you have to take a different path, right? Return path. So it could be something like this. Could be in principle, right? It doesn't matter. So let's say that this is the position from where it started going back. This is the return phase. So I just write tau x2. Okay? This is a different number, this is a different number, right? These are all different numbers. Okay? So you have, as I mentioned before, you have various modes of return. Okay? And generically, if you think about it, so the entire process has two phases, right? One is the original search phase, like where it was just searching, and then it was coming back in 0 time, and then again it was searching, right? Then it was again coming back in 0 time. So we have now slightly generalized this problem, right? We have now said that, okay, we have a search phase, but now also we have a return phase, right? So whenever this return happens with a finite time, tau of x, and it also depends on from where it is being reset. Okay? Okay, so as before, right? So we tried to write a renewal equation for the global completion time, right? So now let us think about the global completion time. Let's say that this is my global completion time, okay? What are the possibilities it will have, okay? First possibility is, okay, here what I didn't do is that after it returned in the second time, let's say that I have again another target here. I could have many targets, right? So then I have this trajectory and then it reached here, okay, after these two return processes, right? And this is my global time. So what are the possibilities? I could have reached directly to one of the targets. There is a possibility that I could have reached without having this resetting, etc., right? So again, it goes back to the same condition. Rather, a very simple condition, right? Now you are understanding what is happening. But now assume that you had a resetting, right? What does it mean? So you were just, like you are having some sort of a motion, some sort of a stochastic motion, and then you came here at this position x1, right? And this is the time when you had this clock, right? You had this resetting clock. It told you that now it's time to go home. Okay. All the other processes we have done so far, we are going back in 0 time. Okay. But in this case, we will take a finite time. Okay. So how I should write? First, I wasted this r amount of time, right? Because this is the one I just diffused all the way. But now after now I got the hint that okay, I have to now go home. So then I need certain time, right? So tau, which is a function of x, right? And then once it goes back to home, let's say that you can have some sort of resting time, etc., some random time, but it's independent. So let us just ignore that time for the time. It doesn't really matter. It is not coupled to anything. It's some rest time. Okay. But then again, the process starts, right? When the process starts, so in the next process, you could again have another return event or multiple return events. So you can again close this stochastic equation by putting tr prime, right? And this is happening with the condition that r is less than equals to t. Same as before, right? So the only ingredient was adding this guy, the finite time, and more critically that it also now depends on from where you are resetting. So what is this x? So x being, in this particular case, let's say the position at the time of resetting. Okay, this is important. Okay, so once we have written this, so next, what is the next step? You guys now understand what is the next step. So we can try to rewrite this equation. So I can just write tr. So minimum of t r. This indicator random variable comes back again. Then you have tau of x, and then you have tr prime. Right? I just rewrote that equation. Okay, you can check that how this is falling into this both of the categories. Okay. So now let me just take the average. So if I take the average over all the possible random quantities, so this happens. So this minimum of tr, this comes out. Then you see there is this guy which has appeared also before, right? So this also comes out. So probability r less than equals to t. Then I have tr average, right? But then there is this guy, I r less than equals to t, tau of x. Okay. Now you see that I cannot take out this guy out, right? I cannot take this guy out. Why? Because this x depends on r, exactly. So I have to keep this guy here. Okay. This is the crucial difference. So let's say that we continue to close the expressions, because I can still, like take this guy on the other side and rewrite the entire expression. Okay, so I can just write. So I have tr. This is minimum of tr, probability t less than r, and then I have this guy. Okay. So this is the contribution from the search phase, and this is the contribution from the return phase. Okay. So this is the search, and this is the return. So this guy is easy to calculate. This guy we have already calculated, right? I have already told you guys how to calculate this. This is trivial. This guy is now critical because this will depend how you are returning, from where you are returning, what is the mode of return. So many different parameters it will depend on. Now let us try to calculate that guy. Okay? So I will take like another 5 minutes or so and then we'll stop. Okay? So let me just erase these. Okay. So what is the goal? So the goal is to calculate this guy, right? So I r less than equals to t tau of x. And anyway, just to make the life simple, so let's just draw a trajectory, 1D trajectory, okay? So I have something like this, right? This is my resetting time, r. This is the position exactly at the time of resetting, x, and from where it returns, right? It returns somewhere, okay? And this is the tau of x, okay? And what I'm looking at, and let's say that I have a global target somewhere here, okay? L. This is my x. And eventually this will keep on happening until it reaches the target, right? Is this schematic clear? Clear, okay. So what are the averages? What is this average quantity? What are the quantities over which I have to average this guy? That I first need to identify, right? So you see that there are 3 quantities I need to average over. First is the time when reset occurred, right? Because this time could be here, anywhere, right? This is coming from a distribution. So if t, right? Second is I also need to average over x, right? Because this x could be anywhere in the space. So I need to average over this x. Okay? So let us try to simplify this. So I r less than equals to t tau of x. Okay? So first I do the average over r. Okay, because that is the first average which is coming, right? Because I had a trajectory. First average is over the waiting time. That is the first thing. So I can just write it in the following sense. So I fixed r t tau x, right? And over what I should average? What did I do here? So I first fixed r, right, which is essentially this guy, this time over here, right? This is what I fixed. R is equal to t, correct? So now I have to average this guy over a for t, right? So a for t. Okay. So now, of course, given this guy, right? Given now this is a fixed. Now inside this average, this is a fixed quantity. So I can immediately take out this I, and if you remember what is I, right? So I is this I of average is like Z1 less than equals to Z2. Average of that was probability that Z1 is less than Z2, right? This is the way we have defined the indicator random variable, right? Which is being used here. So I can just write dt t probability t, right? And then I have tau of x t, right? I still have to average over x, right? But I also need to make sure that this t is less than this t, okay? I'm absolutely sure that it's very confusing, okay? So let me try to convince you guys physically what is happening, okay? From here to here, this is clear, right? Because this t is now fixed, I can take this guy out, right? Because this t is appearing also here, so I can immediately take out this average. There is nothing to average over except for this I. So I take this guy out. So now I have an average over x, right? The only thing which is remaining now, the average over x, right? But I have also written this additional condition, okay? Why did I don't need to write this additional condition if I can keep it in mind, but let me just try to explain what is it. So now the average is over x. This is first I need to understand whether you have understood this, that this average has to be done over x. Clear? Now let us think about it, right? Now this x could be anywhere in the space, right? I also could have an x which has cross tail. Will that average will make any sense? Will not make any sense, right? So I have to make sure, right, that when this resetting occurred, the particle was within the domain of this search, okay, and has not been survived, has not been absorbed, okay. So let us go back to something which we did, like I think we did it like maybe day before yesterday. So we had discussed the fact that if you have an arena, right, and you have some some sort of a boundary through which it escapes, right? So we can still write the probability distribution of the searcher to be found here, right? How do I write it? P of x at a given time, right? Given some starting point, right? But eventually we knew that the particle will be absorbed, right? So we defined this quantity called survival probability. Correct? Now if I have to think about a normalized distribution which ensures the fact that the particle always survives inside, okay? So I am thinking about to construct a probability distribution function which makes sure that I am always inside, okay? Then what should I do? So I have to now construct a new normalized distribution, ensuring this fact that I am actually being survived till time t, right? So this normalized distribution should have this following form. So this P of xt divided by Q of t, okay? And you see that when you normalize this guy, this is 1. Okay? Essentially, like these are all technicalities, whatever, but conceptual level, what is happening is that I have to, when I do this average over x, I have to make sure that the particle is still inside up to time t. This is what is important, okay? Once I do that, so I have this guy, right? So you can write d of x, tau of x, right? Then I can write p of x to given time t, and all this by the survival probability, right? So this is what I have done. I have done an averaging over this normalized distribution. So this essentially ensures that when at the time of resetting, you are still inside the search domain, okay? So now you see that this is actually your survival probability, right? This is something we have calculated. This exactly cancels with this guy, okay? So after this cancellation, what remains is the following. So you have dt t x x x. Okay. So this is all you have from the average of this I function, right? This one. Okay. So I think now like we can plug together all the terms. So now we have TR, which is minimum of T R, T less than R, plus you have this guy. So dt dx tau of x okay. So this is the expression for mean first passage time under finite time resetting. Okay, and just want to finally make these following comments, that if you look into this formula, so it works for any arbitrary resetting distribution in principle. Okay, then also we have not specified what is the underlying search process, right? I have never mentioned that this is a diffusive search or anything. So this is also holds for any arbitrary search process. Okay, then it also depends on, like doesn't matter what kind of mode of return you take, like what is the choice of tau of x you can take, at least formalism level. Practical level, when you put it, you will see what are the implications that might come out. And in principle, you see that although, like it might seem that I have done the derivation for one dimension, this holds for also multiple like higher dimension or so. Okay, and in particular, you have also seen that the phase space I plot, right, the search domain, I had many different targets, right? So there is also nothing specific about one target. You could also have multiple targets in the system. And yeah, and then finally, like in principle, this tau of x could be, at the time being, I have assumed that this to be a deterministic function, but you could also think about what happens when this tau of x itself is a random quantity. Okay, so there are these many things which you can try to understand from this formalism. Okay, so I think I will stop now, and if there are questions, we can continue during the tutorial or tomorrow. Huh? Sorry? Yeah.
No, if there are more questions, we can just take it from the
Yeah.